Hello, friend. Some nights the sky feels different. Not darker, not brighter, just aware. On July 1st, 2025, a telescope in Chile saw something that shouldn't have been there. A tiny point of light moving too fast, coming from the wrong direction. Within hours, scientists around the world confirmed what seemed impossible: we had a visitor. Not from Mars, not from the outer solar system, from somewhere else entirely. A traveler older than our sun, carrying secrets from a star we'll never see. Its name is 3I Atlas, and tonight we're going to ask a question that's both terrible and beautiful. What if it didn't just pass by? Before we drift into this quiet journey together, I want to invite you to stay a while. If these soft explorations bring you comfort, you might like to gently tap the like button. Subscribe if you'd like more stories told this way. And ring the little bell, not for noise, but so the next quiet night can find you again when you need it most. These small gestures help this space exist. Thank you for being here. Now, let's begin. There are roughly 400 billion stars in our galaxy. Between them stretches darkness so complete, so cold, that nothing moves there for millions of years. The space between stars isn't empty. It's filled with ancient debris, frozen gases, and objects that were born around suns that died before Earth even existed. Most of these travelers drift in silence forever, never approaching another star. But sometimes, rarely, one of them finds its way to us. 3I Atlas is only the third interstellar object we've ever detected passing through our solar system. The first was Oumuamua in 2017, strange cigar-shaped, tumbling through space without any visible tail or glow. Scientists argued for months about what it was. The second was 2I Borisov in 2019, clearly a comet with a beautiful tail, streaming behind it looking remarkably similar to comets born in our own solar system. But 3I Atlas is different. It's moving faster than both of them, much faster. When the Atlas Telescope Network first captured it, 3I Atlas was traveling at approximately 130,000 miles per hour. That's 210,000 kilometers per hour. Scientists suggest this is the highest velocity ever recorded for any object visiting our solar system from interstellar space. To put that in perspective, the fastest spacecraft humanity has ever built. Voyager 1, which has been traveling for nearly 50 years, moves at about 38,000 miles per hour. 3I Atlas is moving more than 3 times faster, and it's not slowing down. The designation tells a story in itself. The 3I means it's the third interstellar object officially recognized. The Atlas comes from the telescope system that founded the Asteroid Terrestrial Impact Last Alert System, a network designed to watch for objects that might threaten Earth. Research shows that Atlas scans nearly the entire visible sky every 24 hours, searching for anything that moves in ways it shouldn't. On that July night, something appeared that moved very differently indeed. When astronomers traced its path backward through space, they found something unsettling: 3 eyes. Atlas didn't come from the plane of our solar system where most objects orbit. It came from above at an angle, moving on what scientists call a hyperbolic trajectory. That means it's not bound by the sun's gravity. It's not in orbit. It's just passing through like a stranger walking through your town at night, never planning to return. What makes an object interstellar? It's not just speed, it's the shape of its path. Every planet, asteroid, and comet born in our solar system follows an ellipse, a closed loop around the sun. Even the most distant comets, those that take thousands of years to complete one orbit, still return. But interstellar objects follow open curves, hyperbolas. They come from infinity and return to infinity. Scientists believe 3I Atlas has been traveling through the dark spaces between stars for millions, possibly billions of years. Some preliminary estimates suggest it may be 7 billion years old, older than our entire solar system, which is 4.6 billion years old. Think about that for a moment. 3I Atlas was already ancient when Earth was still a ball of molten rock. It was already drifting through space when the first bacteria appeared in our oceans. It has been moving through the dark longer than complex life has existed on this planet. The discovery happened almost by accident. Atlas wasn't looking for interstellar objects, it was looking for asteroids that might pose a danger to Earth. But the system is automated, comparing images taken hours apart, searching for anything that moves. When 3I Atlas appeared, it moved faster than anything the system had seen before. Within 24 hours, astronomers around the world began pointing their telescopes at it. Within 48 hours, the Minor Planet Center, the organization that officially catalogs space objects, confirmed it was interstellar. Have you ever wondered what it feels like to discover something truly foreign, not just unknown, but from somewhere else entirely? Most mysteries in astronomy involve objects. We understand stars we haven't studied yet, planets we haven't mapped. But interstellar objects are different. They carry information from environments we've never seen. They formed around different stars in different conditions, following different rules. They're messengers in a way, silent letters from distant places. After its discovery, NASA turned nearly every available telescope toward 3I Atlas. The Hubble Space Telescope imaged it in late July. The James Webb Space Telescope studied its chemical composition in August. Multiple spacecraft, Lucy Psyche, Maven, Mars, Reconnaissance Orbiter, ExoMars, Trace, Gas. Orbiter all captured images as the comet passed through the inner solar system. It seems as though humanity collectively held its breath, watching this stranger move through our neighborhood. What they saw was both familiar and strange. 3I Atlas has a coma, a fuzzy cloud of gas and dust surrounding its nucleus. That's normal for comets. As they approach the sun, ice on their surface heats up, turns directly from solid to gas, and carries dust particles with it. The coma glows softly, reflecting sunlight. Behind the coma, a tail forms sometimes millions of kilometers long as solar wind pushes the gas and dust away from the sun. But 3I Atlas showed something unusual. In July and August, and again in early November, it displayed what astronomers call a sunward jet, a stream of material pointing toward the sun, not away from it. This anti-tail puzzled scientists. Some suggested it might be an optical illusion caused by viewing geometry, but detailed analysis showed it was real. Something about 3I Atlas's rotation or internal structure was causing it to eject material in a direction that comets usually don't. The composition of this material was even stranger. Observations from the James Webb Space Telescope revealed that 3I Atlas is exceptionally rich in carbon dioxide, much more than typical solar system comets. It also contains small amounts of water, ice water, vapor carbon monoxide, and carbonyl sulfide. Research shows that its nickel-to-iron ratio is unusually high, suggesting it formed in a region less rich in heavy metals than the area where our solar system was born. The presence of atomic nickel vapor in its coma, something rarely seen in solar system comets, hints at a different chemical environment, a different stellar nursery billions of years ago. Scientists estimate that 3I Atlas's nucleus, the solid core beneath the glowing coma, is somewhere between 440 meters and 5.6 kilometers in diameter. That's a wide range because it's difficult to see the nucleus directly through all the gas and dust. But even at the smaller estimate, it's larger than most near-Earth asteroids we worry about. And it's moving much, much faster. Which brings us to the question we started with. What if it didn't just pass by? What if instead of sailing safely past Earth at a distance of 170 million miles, 3I Atlas had been on a collision course? What if this ancient, fast-moving visitor from another star system had been aimed directly at us? It's not a comfortable question, but it's worth asking. Not because it happened, it didn't. Not because it will happen. The odds are incomprehensibly small. but because asking the question teaches us something important about the universe. We live in the fragility of our world and the strange grace of the fact that we exist at all. 3I Atlas came closest to Earth on December 19th, 2025, just a few weeks from now, as I speak to you. It will be 1.8 times farther from us than the Sun. Completely safe. It poses no danger whatsoever. ESA's Planetary Defense Office confirmed this within days of the discovery. But in another universe with a slightly different trajectory, with a different angle of approach from interstellar space, it could have been different. Impacts happen. They've always happened. The craters on the moon are evidence of billions of years of collisions. Earth has its share too, though erosion and tectonic activity have erased most of them. Meteor crater in Arizona, or 200 meters wide, created by an object only 50 meters across. Vredefort Dome in South Africa, the largest confirmed impact structure on Earth, 300 kilometers wide, created 2 billion years ago. Chicxulub crater in Mexico, hidden beneath the Yucatan Peninsula, where an asteroid ended the age of dinosaurs 66 million years ago. But none of those impacts involved interstellar objects. Every asteroid and comet that has ever struck Earth came from our own solar system. They were neighbors in a sense, family. 3I Atlas would be something else entirely. A collision with a stranger, an impact with no precedent in human history or even in Earth's long memory. The speed makes all the difference. Kinetic energy. The energy of motion increases with the square of velocity. Double the speed, quadruple the energy. 3I Atlas is moving roughly 10 times faster than the asteroid that killed the dinosaurs. Even if it were smaller, the energy of impact would be comparable, and it may not be smaller. Some nights I think about how thin the line is between wonder and catastrophe. The same object can be both depending only on direction. A few degrees of angle and 3I Atlas becomes a light show, beautiful, educational, harmless. A few degrees the other way, and it becomes an extinction event. The universe doesn't care about the difference. Physics doesn't have preferences, but we do. We care. We watch the skies now, not just with curiosity, but with vigilance. Systems like Atlas exist because we've learned to pay attention. We've learned that space isn't just beautiful, it's also dangerous. And we've learned that knowing, seeing, understanding gives us something we've never had before: time. Time to prepare. Time to decide what to do. 3I Atlas is leaving now. By the time you hear these words, it may have already made its closest approach to Earth and begun its long journey back into the dark. It will pass Jupiter in March 2026, still moving at incredible speed. Then it will cross the orbits of Saturn, Uranus, Neptune, and finally slip beyond the edge of our solar system, back into the space between stars. In a few million years, it might pass another star, someone else's sun. Maybe someone will be watching there too. But tonight, while it's still close enough to see through telescopes, while scientists are still gathering data, while the images are still being processed and analyzed, we're going to spend some time with this visitor, not to scare ourselves, not to dramatize danger that doesn't exist, but to understand, to learn what would happen if the universe's aim had been just slightly different, to walk through the physics, the consequences, the human meaning of an impact with something truly foreign. You don't need to be afraid. You're safe. We all are. But there's value in knowing. There's peace strangely in understanding the fragility of this pale blue dot we call home. Because when you understand how rare safety is, how precious each quiet night becomes, gratitude arrives like morning light. Soft, unexpected, true. So, let's drift deeper into the question. Let's meet 3I Atlas properly, not as a threat, but as a teacher. Let's learn what it's made of, where it came from, and what it carries in its ancient frozen heart. To understand what an impact would mean, we first need to know what 3I Atlas actually is. Not what we imagine it to be, not what popular science sometimes makes it sound like, but what the data tells us. what the telescopes see, what the chemistry reveals. Comets are often called dirty snowballs, a description that's both accurate and misleading. Yes, they're made of ice. Yes, they carry dust and rock. But that simple picture misses the profound strangeness of what they are. Comets are time capsules, frozen archives. They contain material that hasn't changed since the solar system was young, preserved in the cold darkness of space for billions of years. When we study a comet, we're reading a message written when planets were still forming. 3 Eyes Atlas carries a message too, but it's written in a different language. It comes from a different library entirely. The nucleus, the solid core at the center of all the glowing gas, is difficult to measure precisely. Scientists suggest its diameter is somewhere between 440 meters and 5.6 kilometers. That range exists because when you look at 3I Atlas through a telescope, you don't see a clean, sharp object. You see a fuzzy blob, the coma, that cloud of gas and dust surrounding the nucleus. It's like trying to measure a light bulb by looking at the glow it produces. You can estimate, but you can't be certain. Using observations from the Hubble Space Telescope taken in August 2025, researchers established lower and upper bounds. The nucleus cannot be smaller than 140 meters, roughly the height of the Empire State Building, because if it were, it wouldn't produce the amount of light and gas we observe. It cannot be larger than 5.6 kilometers, about 3.5 miles, because we would see more light, more activity, a brighter coma. Somewhere in that range lies the truth, a mountain of ice and rock tumbling through space at impossible speed. For comparison, the asteroid that created Meteor Crater in Arizona, that perfect bowl in the desert that tourists visit, was only about 50 meters across. 3I Atlas is at minimum 9 times larger than that. At maximum, more than 100 times larger. Even at the conservative estimate, we're talking about an object with significant mass. And in physics, mass multiplied by velocity squared equals energy. The energy to reshape landscapes, the energy to alter climates, the energy to end eras. But size is only part of the story. What matters just as much is what 3I Atlas is made of. When the James Webb Space Telescope turned its instruments toward 3I Atlas in August 2025, it captured something remarkable: the comet's chemical fingerprint. Every element, every molecule absorbs and emits light at specific wavelengths. By analyzing the spectrum of light coming from the coma, scientists can determine exactly what substances are present. It's like identifying someone by their voice, but using chemistry instead of sound. What Webb found was unexpected. 3I Atlas is exceptionally rich in carbon dioxide CO2, much more so than typical comets born in our solar system. Research shows that solar system comets usually have a higher proportion of water ice and carbon monoxide. The abundance of CO2 in 3I Atlas suggests it formed in a colder region, farther from its parent star, where carbon dioxide could freeze solid. That tells us something about the star system. It came from probably colder, probably with a different distribution of materials than our own. The comet also contains water ice and water vapor, but in smaller quantities than expected. There's carbon monoxide, which is common in space. There's carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur, which appears in volcanic gases on Earth, but is rare in space. And then there's something truly unusual: nickel vapor. Observations from the Very Large Telescope in Chile detected atomic nickel in the coma, individual nickel atoms glowing in sunlight. This is rare, very rare. Most solar system comets don't emit detectable nickel vapor, but 3I Atlas does. Research shows that the nickel-to-iron ratio in 3I Atlas is higher than what we see in comets from our neighborhood. Scientists believe this suggests formation in a region less enriched with heavy metals, perhaps around a star that was older or chemically different than the Sun. Think about what that means. The ratios of elements in 3I Atlas reflect the composition of the molecular cloud that collapsed to form its parent star system. A different ratio means a different starting point. different initial conditions. It's like tasting food from another country and realizing the soil itself was different. The water came from different sources, the sunlight fell at different angles. Everything about 3I Atlas speaks of elsewhere. Another peculiarity, cyanide. Observations detected cyanogen CN in the coma, which is common in comets. But the ratio of nickel to cyanide was unusual. Harvard astronomer Avi Loeb pointed this out in several papers during late 2025, noting that the ratio is similar to what you'd find in industrially produced nickel alloys. He suggested controversially that this might hint at something artificial, something technological. Most scientists disagreed. They argued that chemistry alone can produce these ratios, that we simply don't know enough about how comets form in other star systems to call anything unusual with confidence. But the debate itself is interesting. It shows how little we understand about what's normal for interstellar objects. We've only seen 3. That's not a pattern. That's barely even a sample. We're trying to understand the diversity of an entire galaxy based on 3 visitors. It's like trying to understand all of Earth's cultures by meeting 3 travelers at an airport. The age of 3I Atlas is another mystery wrapped in estimates. Some preliminary calculations suggest it could be as old as 7 billion years. If true, that would make it significantly older than our entire solar system. Our sun is 4.6 billion years old. Earth is roughly the same age. The oldest rocks we found on Earth are about 4 billion years old. 3I Atlas would have already been ancient when Earth was molten, already wandering when the first oceans condensed, already carrying its strange chemistry through the dark. How do scientists estimate age for something like this? They trace its trajectory backward, calculating where it came from. Research shows that 3I Atlas likely originated from the thick disk of the Milky Way, a region populated by older stars that formed when the galaxy was younger and had a different chemical composition. The trajectory aligns with this older stellar population. The chemistry supports it. The speed fits. It seems as though 3I Atlas has been traveling for an incomprehensible amount of time. Now, let's talk about how 3I Atlas compares to the other 2 interstellar objects we've seen. Oumuamua, the first, appeared in October 2017. It was strange from the beginning. Elongated tumbling end over end, showing no coma, no tail, no signs of being a comet. Some scientists suggested it was entirely rock, perhaps a fragment of a shattered planet from another star system. Others proposed it was metallic. Avi Loeb famously suggested it might be artificial, a solar sail perhaps built by an alien civilization. Most astronomers were skeptical, not because the idea was impossible, but because there wasn't enough evidence. Oumuamua left the solar system before we could study it properly. It remains a mystery, an unfinished conversation. 2I Borisov II arrived in August 2019. It was much easier to understand. It looked like a comet. It acted like a comet. It had a bright coma and a long tail. Its composition was similar to comets from our own solar system, lots of water ice, carbon monoxide dust. It seemed as though 2I Borisov came from a place not too different from here. A familiar stranger. 3I Atlas is something in between. It has a coma like Borisov. It shows clear cometary activity. But its chemistry is different. Its speed is higher, much higher. Scientists calculate that 3I Atlas is moving at approximately 58 kilometers per second relative to the Sun. That's faster than Oumuamua, which traveled at about 26 kilometers per second. It's faster than Borisov, which moved at roughly 32 kilometers per second. 3I Atlas is in a hurry, and its mass is staggering by comparison. Research shows that 3I Atlas's nucleus is likely about 1 million times more massive than Oumuamua, and roughly 1,000 times more massive than 2I Borisov. It's not just faster, it's bigger, heavier, carrying more momentum. If momentum is mass times velocity, then 3I Atlas has momentum that dwarfs the other interstellar visitors. There's another oddity worth mentioning: the trajectory. When scientists plotted 3I Atlas's path through the solar system, they noticed something statistically unlikely. The comet's orbit is retrograde. It's moving in the opposite direction from the planets, and it's aligned within 5 degrees of the ecliptic plane. The ecliptic is the flat plane where all the planets orbit. Most objects coming from interstellar space approach from random angles. The galaxy is three-dimensional after all, but 3I Atlas came in nearly aligned with our solar system's plane. Some researchers calculated the probability of this alignment. They found it was about 0.2%, 1 in 500. Not impossible, but unusual. It's like throwing a dart at a globe and hitting a specific latitude line. You could do it by chance, but it makes you wonder. There's also the timing. 3I Atlas made close approaches to Mars within 29 million kilometers and will pass near Venus and Jupiter on its way out. It arrived at a moment when it could be observed by multiple spacecraft at Mars. It appeared in Earth's sky during a period when major telescopes could study it. Some scientists noted that the probability of such convenient timing was very low, perhaps 0.005% or 1 in 20,000. Again, not impossible. Coincidences happen, but the accumulation of small improbabilities is what caught attention. If you see one unlikely thing, you shrug. If you see 12, you start asking questions. Avi Loeb listed 12 anomalies in total: the trajectory, the speed, the mass, the timing, the sunward jet that points the wrong direction, the nickel ratio, the alignment with the ecliptic, the fact that it brightened rapidly, then stabilized, then brightened again in ways that don't quite match typical cometary behavior. Each anomaly alone could be explained. Together, they form a pattern that makes scientists uncomfortable, not because they suggest anything specific, but because they reveal how little we understand. Most astronomers believe 3I Atlas is simply a comet from a different stellar environment behaving according to rules we haven't fully mapped yet. They point out that with only 3 interstellar objects observed, we have no baseline for what's normal. Maybe all interstellar comets are weird. Maybe the universe's creativity exceeds our models. Maybe chemistry operates differently in star systems, with different metallicities, different temperatures, different histories. But the uncertainty itself is important. It reminds us that we're not experts on the universe, we're students, still learning, still surprised. What does all this mean for our question, what if it hit Earth? It means we'd be dealing with an object unlike anything that has ever struck this planet, not just in origin, but in composition behavior speed. Every impact in Earth's history involved material from our own solar system, asteroids made of rock and metal that formed alongside the planets, comets born in the Oort cloud, or Kuiper belt, that have been orbiting the sun for billions of years. We understand those materials, we've studied them. We know how they behave under pressure-heat collision. 3I Atlas would be different. Its ice might sublime differently because of the CO2 abundance. Its structure might be weaker or stronger, depending on how it formed. The release of cyanide and nickel vapor during impact could create chemical reactions we've never observed. The sheer speed would produce temperatures and pressures at the extreme end of anything we've modeled. And yet, for all its strangeness, the 3I Atlas is still bound by the same physics as everything else. Gravity doesn't care where you're from. Energy conservation works the same in every star system. When mass moving at 210,000 kilometers per hour meets a planet, the outcome is determined by equations we understand perfectly well. The strangeness is in the details. The devastation is universal. There's a kind of poetry in that. The universe has infinite variety, different chemistries, different histories, different origins. But the laws remain constant. An interstellar comet obeys the same rules as a raindrop. Both fall, both carry energy, both leave marks when they arrive. So now we know what 3I Atlas is, a mountain of ancient ice and rock, rich in carbon dioxide, laced with nickel and cyanide, moving at record speed, possibly 7 billion years old, definitely foreign, certainly strange, and absolutely real, captured in hundreds of images by dozens of telescopes, studied by thousands of scientists, confirmed beyond any doubt. The question that remains is simpler and harder. Where did it come from? What was its home, like all those billions of years ago before it was thrown into the dark? What kind of star did it orbit? What kind of planets might have shared that system? And what violence, what cosmic event launched it into the void to wander for eons until it reached us? That's where we're going next. Imagine drifting through absolute darkness for 1,000,000 years. No sun, no warmth. Nothing but cold so complete that temperature loses meaning. Now multiply that by 1,000. Now multiply it again. That's the kind of journey 3I Atlas has made. A journey so long that when it began, entire star systems were born, lived, and died along the way. The space between stars isn't empty, but it might as well be. The average distance between stars in our region of the galaxy is about 4 light years. That's roughly 38 trillion kilometers. If you could drive a car at highway speed through space, it would take you 45 million years to reach the nearest star. 3-eyed Atlas has been making that journey not once, but many times over, for longer than complex life has existed on Earth. When astronomers traced its trajectory backward, trying to determine where it came from, they found something both beautiful and lonely. 3I's Atlas appears to originate from the thick disk of the Milky Way. Our galaxy isn't flat like a record. It has structure layers, populations of stars, with different ages and compositions. The thin disk where our sun lives contains younger stars rich in heavier elements. The thick disk above and below the thin disk contains older stars formed when the galaxy was younger and had less chemical diversity. Research shows that 3I Atlas's velocity and trajectory align with the thick disk population. That suggests it came from a region of the galaxy dominated by stars that are billions of years older than our sun. These are ancient stellar systems born when the Milky Way was still settling into its current structure, when supernova explosions were rarer, when the chemical makeup of space was simpler, more hydrogen and helium, fewer heavy metals like iron and nickel. But here's the profound part. We can't point to a specific star and say, that's where it came from. The journey has been too long. Stars move, galaxies rotate. In the time it took 3I Atlas to reach us, its parent star has moved thousands of light years away. It's like trying to find someone's childhood home after they've been walking for 50 years. The house still exists, but the neighborhood has changed, the roads have shifted, and the person doesn't remember the exact address. Scientists estimate cautiously that 3I Atlas may have been traveling through interstellar space for somewhere between a few million and several billion years. The upper estimate 7 billion years would mean it was ejected from its parent system before our sun even existed, before Earth, before the planets. It would have been wandering through the dark while our entire solar system was still just a cloud of gas and dust, slowly collapsing under its own gravity. How does something get ejected from a star system in the first place? It requires violence, specifically gravitational violence. In most star systems, comets and asteroids stay put. They orbit in predictable patterns bound by gravity, but occasionally something disrupts that stability. The most common scenario involves a close encounter with a giant planet, something like Jupiter or Saturn. If a comet passes too close to such a planet, the gravitational interaction can slingshot it outward, accelerating it beyond the star's escape velocity. The comet doesn't crash. It doesn't slow down. It just leaves, thrown into the void like a stone from a sling. This happens in our own solar system occasionally. Scientists believe that Jupiter has ejected countless comets over the past 4 billion years, flinging them into interstellar space. Some of those comets are probably still out there drifting between stars, just like 3I Atlas. Maybe one of them will visit another star system billions of years from now. Maybe someone will see it and wonder where it came from. Maybe they'll calculate its trajectory and realize it points back toward a small yellow star that burned out long ago. Another ejection mechanism involves stellar encounters. When two stars pass close to each other, their gravitational fields can disrupt each other's planetary systems, sending objects flying in all directions. This is more common in dense star clusters, where stars are packed closely together. If 3I Atlas came from such an environment, it might have been ejected not by a planet within its own system, but by a passing star that never belonged there at all. There's also the possibility of binary star systems, two stars orbiting each other. In such systems, the gravitational dynamics are complex. Objects can be flung out in ways that wouldn't happen around a single star. Some scientists suggest that many interstellar objects originate from binary systems, ejected during the chaotic early years when planets and comets were still settling into stable orbits. Whichever mechanism ejected 3I Atlas, the result was the same. It was accelerated to a speed high enough to escape its star's gravity well. Research shows that escaping a star system requires reaching what's called the escape velocity, the minimum speed needed to break free from gravitational binding. For our solar system, escape velocity from the vicinity of Earth's orbit is about 42 kilometers per second. For Jupiter's orbit, it's lower about 18 kilometers per second. The farther out you go, the easier it is to escape. But 3I Atlas isn't just traveling at escape velocity. It's moving at 58 kilometers per second, relative to the Sun much faster. That extra speed didn't come from gravity alone. Something gave it a powerful push. A close encounter with a massive planet, perhaps. Or multiple encounters, each adding momentum until finally the comet reached a speed that carried it into interstellar space. Once in that space, 3I Atlas began the longest, quietest part of its journey. Interstellar space is almost incomprehensibly empty. The average density of matter in the space between stars is about 1 atom per cubic centimeter. By comparison, Earth's atmosphere at sea level contains about 10^19 atoms per cubic centimeter. Interstellar space is a trillion times less dense than the air you're breathing right now. And the temperature, if you can even call it that, is close to absolute zero. The cosmic microwave background radiation, the leftover heat from the Big Bang bathes all of space in a faint glow, equivalent to about 2.7 Kelvin. That's 270 degrees Celsius, 454 degrees Fahrenheit, cold enough that atoms barely vibrate, cold enough that chemical reactions essentially stop. In that environment, 3I Atlas was perfectly preserved. The ices didn't sublime. The chemistry didn't change. It was like an insect trapped in amber, except the amber was the void itself. And the preservation lasted not for thousands of years, but for millions or billions. Every molecule, every crystal structure, every detail of its formation remained frozen in place, waiting. During that journey, 3I Atlas would have been exposed to cosmic rays, high-energy particles that zip through space at nearly the speed of light. These rays slowly damage molecular structures, breaking chemical bonds, creating radiation-altered minerals on the surface. Scientists study this space weathering to estimate how long an object has been exposed. The surface of 3I Atlas probably carries scars from cosmic ray bombardment accumulated over unimaginable spans of time. It would also have passed through the interstellar medium, the thin gas and dust that fills the space between stars. Occasionally, it might have entered denser regions, molecular clouds where new stars are born. In those regions, the density might increase to 10 or even 100 atoms per cubic centimeter, still essentially vacuum by Earth standards, but enough to cause very slight drag over millions of years. That drag would have slowed it down, just barely stealing tiny amounts of momentum with each collision. And yet, despite all that time, despite the cosmic rays and the occasional gas cloud, and the deep, cold 3I Atlas remained intact. It didn't shatter. It didn't evaporate. It simply drifted, patient, silent, carrying its cargo of ancient ice toward a destination it couldn't possibly know was there. Have you ever thought about what it means for something to travel that long without purpose, without awareness? We talk about journeys as if they have meaning, but 3I Atlas wasn't traveling, it was simply moving. Physics doesn't require intention. Objects follow trajectories because that's what mass does in space-time. The comet wasn't brave or determined. It was just cold and small and moving in a straight line as Newton's first law requires. But here's the thing, even though the comet didn't know it was on a journey, we do. We see the arc of its path and recognize it as a story. We trace the line backward through billions of years and feel something like reverence. The universe may not care about meaning, but we do, and in caring, we create it. The fact that we can calculate where 3I Atlas came from even roughly is itself miraculous. We're standing on a small planet looking up at a tiny moving dot and using mathematics to reconstruct a journey that began before dinosaurs, before flowers, before continents as we know them existed. We're reading history written in orbital mechanics. We're listening to a message sent by gravity and time. The Milky Way rotates. Our sun, along with all its planets, is moving through the galaxy at about 230 kilometers per second. We're not sitting still. We're orbiting the galactic center, which is about 26,000 light years away, completing one full orbit every 230 million years. The last time our sun was at this position in the galaxy, dinosaurs were just beginning to evolve. The next time we return here, the sun will be redder, the continents will have different shapes, and whatever species inherits Earth will look up at different stars. 3I Atlas is also moving through the galaxy, but on a different path. It's moving at about 58 kilometers per second relative to the sun, which means its motion through the galaxy is different from ours. Research shows that when you account for the sun's motion and 3I Atlas's motion, the combined picture reveals where their paths diverged somewhere in the thick disk billions of years ago, when both were in different parts of the galaxy entirely. Here's a thought that keeps astronomers awake at night. There are probably millions, maybe billions of objects like 3I Atlas drifting through interstellar space right now. Most of them will never encounter another star. They'll just drift forever, silent and frozen, carrying stories no one will ever read. We only see the ones that happen to pass close enough to our sun to be detected. We're sampling an invisible population, catching glimpses of wanderers who happen to cross our path. Some scientists estimate that there might be more interstellar objects in the galaxy than there are stars. Every star system ejects comets and asteroids. Over billions of years, those ejections add up. The space between stars becomes populated with ancient debris, all of it moving, all of it carrying chemical fingerprints from different environments, different eras. In a way, interstellar space is a museum, or a cemetery, or both. It's where the lost things go. The objects that were part of planetary systems, once that orbited young stars, when the galaxy was different, that perhaps witnessed the formation of planets that still exist somewhere unreachably far away. 3I Atlas is one artifact from that museum temporarily on display in our neighborhood. There's a loneliness to that image, but also a kind of connection. Every star system contributes to this wandering population. Every system receives visitors in return. The galaxy is constantly shuffling its material, sending messengers from one corner to another, even if those messages take millions of years to arrive. 3I Atlas came from somewhere. Maybe it passed other star systems along the way too distant to notice. Maybe it will pass others after leaving us. The journey isn't over. When 3I Atlas leaves our solar system, which it will soon, it will return to the darkness. It will continue moving at its incredible speed, gradually slowed by the faint drag of interstellar gas, but not by much. In a few million years, it might pass within a light year of another star. If that star has planets, and if those planets have astronomers, they might see it too. They might study it, measure its chemistry, calculate its trajectory, and realize, as we did, that it came from elsewhere. and they might wonder as we do what it would mean if it hit them. But for now, 3I Atlas is here, passing through our small corner of the galaxy, visible in our telescopes for this brief moment. It arrived from the deep past, carrying ice from another star system, moving on a trajectory set millions or billions of years ago. It's the most foreign object we've ever studied up close, a genuine alien, not in the sense of intelligent life, but in the deeper sense other, different, from somewhere we'll never see. That otherness is about to meet our world in the most violent way physics allows. Because now that we understand what 3I Atlas is and where it came from, we can finally ask the question that matters most. What happens when an ancient traveler moving at 210,000 kilometers per hour encounters a planet that wasn't expecting visitors? Energy doesn't care about intentions. It doesn't ask where you came from or what you're made of. It only cares about mass and velocity. And when you multiply the mass of a mountain by the square of 210,000 kilometers per hour, the answer is written in fire and shockwaves and geological time. Let's do the mathematics quietly, like counting stars. If we assume 3I Atlas has a nucleus approximately 2 kilometers in diameter, a middle estimate between the upper and lower bounds, and if we assume its density is similar to other comets, roughly 600 kilograms per cubic meter, then we can calculate its mass. The volume of a sphere is 4/3 pi times the radius cubed. A 2-kilometer diameter gives us a radius of 1 kilometer, or 1,000 meters. The volume comes out to about 4.2 billion cubic meters. Multiply by density, and we get a mass of approximately 2.5 billion metric tons. That's the mass of about 12,500 Empire State Buildings, or 350 million full school buses, or one Mount Everest if you could somehow pick it up and throw it. Now, for the velocity. 3I Atlas is moving at 210,000 kilometers per hour, which is 58.3 kilometers per second. Kinetic energy. The energy of motion is calculated as 1/2 times mass times velocity squared. When you plug in the numbers, the result is staggering, approximately 4.2x × 121 joules. Numbers at that scale lose meaning quickly, so let's translate. 1 megaton of TNT, the unit used to measure nuclear weapons, releases about 4.2 × 1015 joules. The atomic bomb dropped on Hiroshima in 1945 was approximately 15 kilotons, or 0.015 megatons. The largest nuclear weapon ever tested, the Soviet Tsar Bomba in 1961, was 50 megatons. It was so powerful that its shockwaves circled the Earth 3 times. The flash was visible from 1,000 kilometers away. Windows shattered in Finland. The impact of 3I Atlas would release approximately 1 million megatons of energy. That's 20,000 times more powerful than Tsar Bomba. It's roughly equivalent to all the nuclear weapons on Earth, detonating simultaneously not once, but several times over. But even that comparison doesn't quite capture it. Nuclear weapons release energy through fission or fusion, breaking apart atoms or fusing them together. Impact energy is purely kinetic. It's the energy of motion converting instantly into heat pressure and shock waves. The physics is simpler, the devastation is not. To understand what that energy does, we need to compare 3I Atlas to impacts we know actually happened. 66 million years ago, an asteroid approximately 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, about 180 kilometers wide and 20 kilometers deep. The energy released was estimated at 100 million megatons, about 100 times more powerful than our hypothetical 3I Atlas impact. That collision ended the Cretaceous period. It killed the non-avian dinosaurs. It triggered wildfires across continents. It threw so much dust into the atmosphere that sunlight dimmed for years, causing a collapse in photosynthesis and a mass extinction that eliminated roughly 75% of all species on Earth. So in comparison, 3I Atlas is smaller, much smaller. But here's the critical detail that makes it uniquely dangerous speed. The Chicxulub impactor was moving at an estimated 20 kilometers per second, typical for asteroids in our solar system. 3I Atlas is moving at 58 kilometers per second, nearly 3 times faster. When velocity is squared in the kinetic energy equation, that difference becomes enormous. Even though 3I Atlas has less mass, perhaps 1,000th the mass of the Chicxulub asteroid, its speed partially compensates. The result is an impact that, while not globally catastrophic in the way Chicxulub was, would still be devastating on a regional or continental scale. Scientists estimate that 3I Atlas would release enough energy to rank among the most powerful geological events in modern human history. Not as powerful as the supervolcano eruption at Toba 74,000 solar years ago, which may have reduced the human population to a few thousand individuals. Not as powerful as the Thera eruption in 1600 BCA, which may have contributed to the collapse of the Minoan civilization, but comparable to the largest volcanic eruptions recorded in historical times. The eruption of Mount Tambora in Indonesia in 1815 ejected approximately 160 cubic kilometers of ash and rock. It was the largest volcanic eruption in recorded history. The following year became known as the Year Without Summer. Crops failed across Europe and North America, snow fell in June. Temperatures dropped globally. Tens of thousands died from famine. The eruption released an estimated 800 megatons of energy. 3I Atlas carries more than 1,000 times that energy. Here's a thought experiment. Imagine 3I Atlas striking in the middle of the Atlantic Ocean, halfway between North America and Europe. What happens in the first second contact? The leading edge of the comet meets the ocean surface at 58 kilometers per second. At that speed, water doesn't behave like a liquid. It behaves like a solid wall. The comet begins to compress, but so does the water. Both are subjected to pressures measured in millions of atmospheres. The temperature at the point of contact instantly exceeds 10,000 degrees Celsius, hotter than the surface of the sun. In the first millisecond, a shockwave propagates through both the comet and the water. The comet, made of ice and rock, begins to vaporize. The water, subjected to impossible pressures, turns into a superheated plasma. Light visible ultraviolet infrared flashes outward. If anyone were watching from a safe distance, they would see the ocean suddenly glow brighter than a welder's torch. Within the first tenth of a second, the comet has penetrated kilometers into the ocean. It's no longer a solid object. It's a column of expanding plasma, pushing aside water, drilling downward. The energy transfer is so rapid that the water can't flow out of the way fast enough. It's compressed, superheated, and ejected upward and outward in a massive expanding bubble. By the time 1 full second has passed, the comet has reached the ocean floor, perhaps 4 or 5 kilometers down, depending on the depth at the impact site. The seafloor, made of basalt and sediment, is struck with the force of 1,000,000 nuclear weapons. Rock vaporizes. A crater begins to form, not through erosion or excavation, but through sheer shock compression. The rock doesn't have time to crack or shatter. It simply melts and flows like water. Within 10 seconds, the crater is fully formed. It's roughly 15 to 20 kilometers wide, depending on the exact mass and velocity of the comet. The crater is deep, perhaps 5 kilometers or more, and its walls are molten. Around the crater, a shock wave is propagating through the Earth's crust, a seismic pulse equivalent to a magnitude 9 earthquake. If the impact occurred on land, that shock wave would be felt thousands of kilometers away. Buildings would collapse, roads would buckle, landslides would cascade down mountains. But we place this impact in the ocean, which adds another layer of horror tsunamis. The displaced water, billions of tons of it, is thrown outward in all directions. Research shows that impact-generated tsunamis are different from earthquake-generated tsunamis. Earthquake tsunamis are caused by vertical displacement of the seafloor. One section rises, another falls, and the water above it is pushed into motion. Impact tsunamis are caused by something much more violent, a massive cavity opening in the ocean, then collapsing back in on itself, sending waves radiating outward at hundreds of kilometers per hour. The initial wave height near the impact site might be a kilometer or more, a wall of water taller than the tallest skyscrapers moving faster than a jet airplane. As the wave travels across the ocean, it spreads out, losing height but maintaining energy. By the time it reaches coastlines, say the eastern seaboard of North America or the western coast of Europe, it might be 30 to 50 meters high. That's taller than a 10-story building moving inland at highway speeds, carrying debris vehicle structures. Coastal cities would have warning. Seismometers would detect the impact immediately. Satellite surveillance would see the flash. Tsunami warning systems would activate. But the time between warning and impact might be only an hour or two, depending on distance. That's not enough time to evacuate millions of people from major urban centers. New York, Boston, Miami, London, Lisbon, all would face inundation. Historical tsunamis give us some sense of scale, but nothing quite matches an impact scenario. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake, killed approximately 230,000 people across 14 countries. The waves were 10 to 30 meters high when they reached coastlines. The 2011 Tohoku tsunami in Japan, triggered by a magnitude 9.0 earthquake, reached heights of 40 meters, and some locations traveled up to 10 kilometers inland and killed nearly 20,000 people. An impact tsunami would be worse. Not just taller, but faster, carrying more energy, affecting a larger area. If 3I Atlas struck in the Atlantic, both sides of the ocean would be affected. If it struck in the Pacific, every coastline around the Pacific Rim, Japan, China, the Philippines, Indonesia, Australia, the Americas would face devastation. Now, imagine the impact occurs on land. Let's say it strikes in the Great Plains of North America, a flat, relatively unpopulated region, but close enough to major cities to illustrate the consequences. The initial flash of light would be visible from space, a point on the Earth's surface suddenly glowing like a second sun. Satellites would be blinded temporarily. Anyone within direct line of sight, hundreds of kilometers away, would see the flash. Some would be curious. Most wouldn't have time to wonder what it was before the next effects arrived. Thermal radiation heat carried by light would spread outward at the speed of light. Within a radius of perhaps 50 kilometers from the impact site, everything exposed to the sky would be subjected to temperatures sufficient to ignite wood-melt plastic and cause third-degree burns on exposed skin. It would be like standing next to an open blast furnace, but the furnace is the size of a city, and the heat lasts for several seconds. Then comes the shockwave. Sound travels at about 340 meters per second in air. But the shockwave from an impact isn't sound, it's a pressure wave moving faster than sound, compressing the air itself. Scientists suggest that close to the impact site, the overpressure, the increase in atmospheric pressure would exceed 10 atmospheres. That's enough to collapse most buildings instantly. Concrete structures would crumble, steel frames would buckle, wooden houses would disintegrate into splinters. The shock wave would propagate outward in an expanding circle, weakening with distance, but remaining deadly for hundreds of kilometers. At a distance of 200 kilometers, the overpressure might still be enough to shatter windows, knock people off their feet, and cause severe structural damage to buildings. At 500 kilometers, you might experience a sudden gust of wind, a loud boom, and broken glass. At 1,000 kilometers, you'd hear a distant rumble, feel the ground shake slightly, and wonder what just happened. For comparison, the largest conventional explosions in human history, accidental detonations of munitions, stockpiles, industrial accidents produced shock waves that shattered windows up to 20 or 30 kilometers away. The Halifax explosion in 1917, when a ship carrying 2,900 tons of explosives detonated in the harbor, was heard 400 kilometers away and broke windows up to 80 kilometers away. It killed nearly 2,000 people and injured 9,000 more. 3I Atlas carries energy equivalent to hundreds of thousands of Halifax explosions. The shockwave would be felt across an entire continent. But the immediate destruction, the flash, the shockwave, the crater is only the beginning. The real question is, what happens to the ejecta, the material thrown into the atmosphere by the impact? When a high-velocity object strikes the Earth, it doesn't just make a hole, it excavates. Rock and soil are thrown upward and outward at tremendous speeds. Some of this material falls back near the crater, forming an ejecta blanket, but a significant portion is thrown high enough and fast enough to reach the upper atmosphere or even escape into space temporarily before falling back. Research shows that the amount of ejecta depends on the impact energy and the target material. A rough estimate for 3I Atlas suggests that several hundred cubic kilometers of rock soil and vaporized comet material would be ejected. Some of this material would be heated to thousands of degrees during ejection, turning into molten droplets or even vapor. As it re-enters the atmosphere, it would heat the air, creating secondary shock waves and intense thermal radiation. In the minutes and hours following the impact, much of this material would fall back to Earth. Close to the impact site, within a few hundred kilometers, the ground would be buried under meters of hot debris. Farther away, the debris would fall as a rain of small particles still hot enough to ignite fires. Forests would burn. Grasslands would become infernos. Cities far from the impact site might escape the shockwave only to face wildfires started by falling debris. And then there's the dust. Fine particles smaller than grains of sand, smaller than pollen, would be carried into the stratosphere by the heat and violence of the impact. Unlike material ejected ballistically, which falls back quickly, stratospheric dust remains aloft for months or even years. It forms a thin veil around the planet, reflecting sunlight back into space, cooling the surface. This is the mechanism that made the Chicxulub impact so deadly. The immediate destruction was regional. The dust cloud was global. Temperatures dropped. Photosynthesis slowed. Food chains collapsed. The dinosaurs didn't die from the shockwave, they died from starvation and cold in the months and years that followed. 3I Atlas wouldn't produce a global extinction. The dust injection would be smaller, the cooling would be less severe, but it would still matter. Scientists estimate that a 1 million megaton impact could inject enough dust to cool global temperatures by 2 to 5 degrees Celsius for several months. That might not sound like much, but it's enough to disrupt growing seasons, damage crops, and cause food shortages in regions already vulnerable to climate variability. There's also the question of what happens chemically. Impacts generate enormous heat, which causes nitrogen and oxygen in the atmosphere to combine, forming nitrogen oxides. These compounds, when dissolved in water, create nitric acid rain. The Chicxulub impact is thought to have produced acid rain strong enough to acidify the oceans and kill marine organisms. 3I Atlas would produce similar effects, though less extreme. Here's something most people miss when they think about impacts the Earth doesn't forget. Long after the fires are extinguished, long after the dust settles, long after the tsunamis recede, the planet carries a scar. The crater remains slowly eroding, but visible for millions of years. The chemical signature, unusual concentrations of elements like iridium brought by the impactor, remains in the geological record. Future geologists digging through rock layers would find a thin line marking the moment when something from elsewhere arrived uninvited. We've never experienced an impact of this scale in recorded history. The closest we've come, the Tunguska event in Siberia in 1908, involved an object perhaps 50 to 100 meters across that exploded in the air before reaching the ground. It flattened 2,000 square kilometers of forest. It was equivalent to about 10 to 15 megatons. No one died because the region was uninhabited. But if it had occurred over a city, the death toll would have been in the hundreds of thousands. The Chelyabinsk meteor in 2013 was smaller still, about 20 meters across, and it exploded at an altitude of 30 kilometers. The shockwave injured more than 1,500 people, mostly from broken glass. The flash was brighter than the sun. Dashcam videos captured the moment, an ordinary morning, suddenly interrupted by light and sound and confusion. Now, imagine something 100 or 1,000 times more powerful. Not a small rock exploding in the atmosphere, but a mountain of ice and stone striking the surface, releasing energy that would reshape coastlines, alter climates, and end countless lives in the span of seconds. It's not fear we're cultivating here. It's respect. Respect for the forces that shape planets. Respect for the fragility of the thin layer of air and water and life that makes Earth habitable. Respect for the fact that we exist in a shooting gallery surrounded by objects moving at impossible speeds, most of which miss us, but some of which eventually might not. The atmosphere itself would remember, for years. And in that memory written in particles too small to see would be the story of what happens when an ancient traveler finally arrives, not as a guest, but as a force of nature too powerful to resist. Before 3I Atlas ever touches the ground, the sky itself begins to burn. The atmosphere is not empty space. It's an ocean of gas, 100 kilometers deep, pressing down on everything with the weight of 10 meters of water. When something moving at 58 kilometers per second tries to pass through that ocean, the air doesn't have time to move aside. It compresses, and compressed air heats up, not gradually, but explosively, reaching temperatures that would vaporize steel in milliseconds. Entry isn't gentle, it's violence translated into light. Imagine standing on a beach at dawn watching the eastern horizon. The sky is the soft blue of early morning. Birds call, waves roll in with their eternal rhythm. And then, without warning, a second sun appears directly overhead. Not rising from the horizon like the real sun, but simply there, impossibly bright, brighter than anything you've ever seen. Your shadow on the sand becomes sharp and dark. The temperature on your skin rises noticeably. You look up instinctively foolishly, and the light sears your retinas before you can look away. That light is 3I Atlas announcing its arrival. When the comet enters Earth's atmosphere, it's still at its full interstellar velocity, 210,000 kilometers per hour. At that speed, it crosses the distance from the edge of space to the ground in less than 2 seconds. But those 2 seconds contain an entire cascade of physics, each stage more violent than the last. The first effect is compression heating. As 3I Atlas plunges downward, the air in front of it can't escape fast enough. It piles up, compressing into a thin shell of superheated gas. Research shows that compression heating at hypersonic speeds can produce temperatures exceeding 10,000 Kelvin, that's 9,700 degrees Celsius, or 17,500 degrees Fahrenheit. For comparison, the surface of the sun is about 5,800 Kelvin. The leading edge of 3I Atlas during entry is hotter than the sun's surface. At these temperatures, air itself begins to change. Nitrogen and oxygen molecules, which normally bond as N2 and O2, break apart into individual atoms. Some of those atoms ionize, they lose electrons, becoming electrically charged. The result is a plasma, a state of matter where electrons float freely among atomic nuclei, creating a glowing electrically conductive fluid. This plasma sheath surrounds 3I Atlas like a cocoon of fire. The light emitted by this plasma isn't just visible light, it spans the entire electromagnetic spectrum. Ultraviolet radiation intense enough to cause instant sunburn at ground level. Infrared radiation felt as heat. Radio waves which would temporarily disrupt communication systems in the region. Anyone looking at the sky would see not a discrete object, but a streak of incandescent light like a welding arc drawn across the heavens. The Chelyabinsk meteor in 2013 gives us a small preview. That object was only about 20 meters across a pebble compared to 3I Atlas, and it entered at 19 kilometers per second, about a third the speed. When it exploded in the atmosphere, the flash was brighter than the sun for observers on the ground. Dash cam footage shows ordinary morning commutes suddenly flooded with white light shadows, vanishing colors washing out. People stopped their cars. Some thought a nuclear weapon had detonated. Others thought the world was ending. One witness described it as though the sky had become a second floor, and someone had opened a door to a furnace on the other side. The light didn't fade, it blazed held, then slowly dimmed as the meteor fragmented and dispersed. The entire event lasted about 30 seconds. The brightness peak lasted perhaps 3 seconds. In those 3 seconds, more than 1,500 people were injured, mostly from broken glass as windows shattered from the delayed shockwave. Now scale that up by a factor of 1,000 or more. 3i Atlas wouldn't just brighten the sky, it would turn the sky into a weapon. Thermal radiation travels at the speed of light, which means it arrives before the shockwave, before the sound, before anyone understands what's happening. Within direct line of sight of the entry path, potentially hundreds of kilometers on either side, depending on atmospheric conditions, surfaces exposed to the sky would suddenly be subjected to radiant heat, comparable to standing close to an industrial furnace. Scientists estimate that thermal radiation from a large impact can deliver energy densities of several calories per square centimeter per second. That might sound abstract, so let's translate. 1 calorie per square centimeter is enough to cause first-degree burns on human skin, redness pain, but no blistering. 3 to 5 calories per square centimeter causes second-degree burns, blistering, severe pain, permanent scarring. 10 calories per square centimeter causes third-degree burns, complete destruction of skin layers, nerve damage, life-threatening injuries. 3i Atlas, during its 2-second entry, could deliver 15 to 20 calories per square centimeter to surfaces within 200 kilometers of its path. Trees would ignite, dry grass would burst into flame, wooden structures would begin to smolder. Anyone caught outside looking at the sky would suffer severe burns on exposed skin within seconds. Clothing would catch fire. Paint on buildings would blister and peel, but most people wouldn't be looking up. Most people would be inside, going about their lives unaware. And the walls that protect them from wind and rain would also protect them from the thermal pulse, at least initially. It's the indirect effects that spread the danger. Wildfires would ignite across the landscape, not from the impact itself, but from the thermal radiation during entry. Research shows that a single large impact can start thousands of simultaneous ignition points over an area of hundreds of thousands of square kilometers. These fires wouldn't spread from a single source. They would appear spontaneously in forests, grasslands, near buildings all at once. Firefighting resources already strained by the scale of the disaster would be overwhelmed instantly. Historical wildfires give us some sense of what this means. The 1871 Peshtigo fire in Wisconsin, which occurred on the same night as the Great Chicago Fire, burned 1.2 million acres and killed at least 1,500 people, possibly many more. The fire moved so fast that people couldn't outrun it. Survivors described the walls of flame taller than buildings, heat so intense that sand melted into glass. The fire created its own weather, generating tornado-like vortices that threw burning debris kilometers ahead of the main front. The Black Saturday bushfires in Australia in 2009 killed 173 people and burned 450,000 hectares. Wind speeds exceeded 100 kilometers per hour. Flames reached 30 meters high. The radiant heat was so intense that firefighters couldn't approach within 100 meters of the fire front. Some victims were found inside cars that had melted around them. Now, imagine fires of that intensity, but starting simultaneously across an area the size of Texas or France, not advancing from one direction, but erupting in every direction at once. The smoke alone would darken the sky, creating an artificial twilight that could last for days. But before the fires matter, before the smoke matters, there's the shockwave. Sound is a pressure wave traveling through air. It moves at about 340 meters per second at sea level, about 235 kilometers per hour. When an object moves faster than sound, it creates a sonic boom, a shock wave where pressure discontinuously jumps from normal atmospheric pressure to a higher value, then drops back. Anyone who's heard a supersonic jet pass overhead knows the sound, a sharp crack, sometimes a double boom that rattles windows and startles birds. 3I Atlas is moving at Mach 170 times the speed of sound. The shock wave it generates isn't a polite sonic boom. It's a wall of compressed air, a moving discontinuity in pressure and density so abrupt that the air itself becomes briefly opaque. The technical term is a bow shock. It forms in front of the comet, shaped like a cone with the comet at its apex. Inside this cone, the air is compressed to several times normal density and heated to thousands of degrees. Outside the cone, the air is still undisturbed, unaware that anything is coming. The boundary between these regions is razor thin, just a few molecular mean free paths, which at atmospheric density is about 1/millionth of a meter. As 3 Atlas descends, this bow shock sweeps across the landscape like an invisible blade. Trees bend, buildings shudder, lakes ripple, and then half a second later, the shock wave reflects off the ground and follows a second pulse of overpressure that reinforces the first. The Tunguska event in 1908 provides our best terrestrial example. An object, probably a small asteroid or comet fragment, exploded in the air over Siberia at an altitude of about 5 to 10 kilometers. It never reached the ground. The airburst alone flattened 2,000 square kilometers of forest, knocking down an estimated 80 million trees in a radial pattern extending 30 kilometers from the blast center. Witnesses 65 kilometers away were knocked off their feet by the shockwave. Windows broke 200 kilometers away. Seismographs in Western Europe recorded the event. Atmospheric pressure waves circled the globe twice. Night skies across Europe and Asia glowed for several days. Afterward, an effect scientists suggest was caused by dust and water vapor in the upper atmosphere scattering sunlight. The Tunguska object was perhaps 50 to 100 meters across. Its energy at detonation was estimated at 10 to 15 megatons. 3I Atlas carries energy 100,000 times greater and won't explode in the air. It will reach the ground intact, or nearly so, because its mass and density give it enough momentum to punch through the entire atmosphere without fragmenting. The shock wave from 3I Atlas would be felt as a sudden violent gust of wind, except wind implies air moving from high pressure to low pressure. This is different. This is pressure itself, moving a wave of compression, propagating outward from the entry path. The force would be measured not in wind speed, but in overpressure. The difference between the pressure in the shock wave and normal atmospheric pressure. Research shows that an overpressure of just 0.1 atmospheres, 10% above normal, is enough to shatter windows. At 0.3 atmospheres, residential buildings suffer structural damage. At 1 atmosphere, double the normal pressure, most buildings collapse. Above 2 atmospheres, even reinforced concrete structures fail. Close to the impact trajectory, overpressures could reach 5 to 10 atmospheres. That's equivalent to being 50 to 100 meters underwater, except the pressure arrives in a fraction of a second. Human bodies subjected to that kind of sudden pressure change don't survive intact. Eardrums rupture, lungs collapse, blood vessels burst. It's not the heat or the light, it's simply the force of air moving faster than anything should move. Farther from the trajectory, 100 to 200 kilometers away, the overpressure drops to more survivable levels, but the effects are still catastrophic. Buildings lose roofs, walls crack. Anyone caught outside would be thrown to the ground. Debris becomes shrapnel. Cars overturn. Trees snap. There's a delay, of course. Light travels instantaneously, so the thermal pulse arrives first. Then comes the shockwave, moving at the speed of sound, or faster initially, because it's a supersonic shock. If you were 200 kilometers from the impact point, you'd see the light first feel the heat, and then 10 minutes later, hear and feel the arrival of the shockwave. Those 10 minutes would be strange. The sky would be bright. Fires might already be starting. Birds would be fleeing, and then the air itself would hit you like a freight train. After the primary shockwave passes, there's a secondary effect, the wind reversal. Shockwaves compress air as they pass, pushing it in the direction of travel. But once the shock front has moved on, that compressed air expands back, creating a temporary low-pressure region and a strong wind blowing in the opposite direction. This blast wind can last for tens of seconds, carrying dust debris and anything not secured. In nuclear explosions, the blast wind is often more destructive than the initial shock wave because it lasts longer and can topple structures already weakened by the primary pulse. For 3I Atlas, the blast wind would turn the landscape into a sandblaster. Loose soil, gravel, leaves, broken glass, everything becomes airborne, moving at hurricane speeds. Visibility drops to zero. Breathing becomes difficult. The world turns into chaos, written in dust and noise. And throughout all of this, the light, the heat, the shock wave, the wind, the atmosphere itself is changing chemically. High temperatures cause nitrogen and oxygen to react, forming nitrogen oxides, NO and NO2. These compounds are normally rare in the atmosphere, but impacts generate them in enormous quantities. When dissolved in water, rain fog, even morning dew, they form nitric acid. The result is acid rain. With a pH low enough to damage, plants contaminate water supplies and corrode metal structures. After the Chicxulub impact, scientists estimate that acid rain fell globally for months. The ocean's surface layer became acidified, killing plankton and disrupting marine food webs. On land, plants suffered leaf damage. Soils became toxic. The effect wasn't as dramatic as the fires or the cold, but it lasted longer and affected ecosystems that otherwise might have survived. 3I Atlas would produce similar chemistry, though on a smaller scale. Regional acid rain perhaps rather than global, but combined with fire's dust and physical destruction, it would add another layer of ecological stress to an already overwhelmed system. There's also the question of what happens to the comet material itself during entry. 3I Atlas is made primarily of water ice and carbon dioxide ice with dust and rock mixed in. As it enters the atmosphere, the outer layers begin to ablate, literally vaporize from the heat. This creates a trail of gas and dust, extending along the entire entry path from 100 kilometers altitude down to the ground. That trail glows. Not just from reflected sunlight, but from self-emission. The heat of vaporization is so intense that the vapor itself radiates light. Observers hundreds of kilometers away would see a luminous contrail like a scratch across the sky, hanging in the air for several minutes after the impact. The trail would be visible even in daylight, a testament to temperatures and energies that don't belong in Earth's atmosphere. Some of the vaporized material would reach the stratosphere, joining the dust and smoke already being pumped up by fires and the impact itself. Water vapor in the stratosphere has interesting effects. It enhances the formation of polar stratospheric clouds, which can contribute to ozone depletion. Cyanide and other exotic chemicals from the comet would be diluted and dispersed, but traces would remain detectable in ice cores and atmospheric samples for years afterward. Have you ever watched a thunderstorm build in summer? The way the sky changes color, the way the air feels electric, the way birds go quiet, and the world seems to hold its breath. That's a small taste of what the atmosphere feels like when it's stressed. An impact of this scale doesn't just stress the atmosphere, it traumatizes it. The sky itself remembers in particles and chemistry and pressure waves that echo for days. And all of this, the light, the heat, the shock wave, the fires, the chemical changes happens before the comet reaches the ground. The entry phase lasting just seconds, sets the stage for everything that follows. It's the opening act of a disaster whose full scale won't be understood for hours, days, weeks. But now the comet has crossed those final kilometers. The atmosphere has done what it can, stealing energy, fragmenting smaller meteorites, slowing objects that are light enough to be slowed. 3I Atlas, massive and fast, has barely noticed. It arrives at the surface with most of its velocity intact, carrying energy that will reshape the landscape in ways that take geological time to heal. The ground itself is about to learn what it means to be struck by something from elsewhere. Contact lasts less than a second, but the scar lasts millions of years. When 3I Atlas strikes the Earth's surface, let's say it hits land somewhere in the continental interior, far from cities, but close enough that millions will feel the consequences. The ground doesn't crack or shatter the way you might imagine. It doesn't have time. At 58 kilometers per second, rock behaves like a fluid. Solid granite, billions of years old, flows like water under pressures that exist nowhere else on Earth, except perhaps in the planet's core. The physics of crater formation happens in stages, each lasting fractions of a second, each governed by forces so extreme they seem almost abstract until you see the results written in the landscape. The first stage is called contact and compression. The leading edge of the comet meets the surface. In that instant, measured in milliseconds, both the comet and the ground begin to compress. The comet, made of ice and rock, is denser than air, but much less dense than solid granite. It starts to deform, crumple like a car hitting a wall at impossible speed. But the wall is also deforming. The rock beneath the impact point is compressed to several times its normal density, heated to tens of thousands of degrees, and subjected to pressures exceeding 1 million atmospheres. Research shows that at these pressures, rock enters what's called a shocked state. Its crystal structure changes. Minerals transform into high-pressure phases that don't normally exist at Earth's surface. Quartz becomes coesite or stishovite. Feldspar melts outright. Carbon, if present, can transform into diamond. These shocked minerals are diagnostic. When geologists find them, they know an impact occurred there, even if the crater has long since eroded away. Within the first tenth of a second, a shockwave begins propagating downward and outward through the rock. This isn't a seismic wave, not yet. It's a shock front similar to the bow shock that formed in the atmosphere, but moving through solid material. Behind the shock front, the rock is compressed, heated, and moving. Ahead of it, the rock is still at rest, unaware. The shock front moves faster than seismic waves, perhaps 10 to 15 kilometers per second through granite. It travels downward, reaching depths of several kilometers, and outward, weakening as it spreads. The energy carried by the shock is what excavates the crater. It doesn't blast material away, like an explosion in air. Instead, it sets the rock in motion, creating a flow field where solid stone moves like a slow-motion liquid. By 1 second after impact, the transient crater has formed. This is the initial hole, deeper and narrower than the final crater will be. Imagine a bowl roughly 10 kilometers across and 3 to 4 kilometers deep, though these numbers depend on the exact impact angle, velocity, and geology of the target. The walls of this transient crater are nearly vertical, and they're unstable. Gravity immediately begins pulling them inward. Here's where crater formation becomes counterintuitive. You might expect the crater to stay the shape it was blasted into, but craters aren't static. They're dynamic, evolving under gravity even as they form. The floor of the transient crater rebounds, literally springs back upward, because the rock beneath it has been compressed like a spring and then suddenly released. This rebound can lift material from several kilometers deep back up to the surface, creating what's called a central peak. If you've ever dropped a stone into water and watched in slow motion, you've seen this process. The water splashes outward, then a column rises in the center, a spike of liquid reaching upward before collapsing back. Craters do the same thing, except the liquid is rock and the process takes minutes instead of milliseconds. Some of Earth's most beautiful impact craters have prominent central peaks. Meteor Crater in Arizona doesn't, it's too small, but larger craters like Manicouagan in Canada or Goss's Bluff in Australia show clear central uplifts. These peaks contain rock that was once kilometers underground, brought to the surface by the violence of impact and the elastic response of the Earth's crust. For 3I Atlas, the rebound would be substantial. The central peak might rise a kilometer or more above the crater floor before collapsing back into a complex central uplift. And as the crater walls slump inward under gravity, the crater widens and shallows. The final crater, the one that remains after the dust settles, might be 15 to 20 kilometers in diameter, and perhaps 1 to 2 kilometers deep. Not as deep as the transient crater, but much wider. The shape would be roughly circular, regardless of the angle of impact. This surprises people. They imagine that a comet hitting at an angle would create an elliptical crater, like a bullet striking at an angle makes an elongated hole. But impacts are so energetic that the direction matters less than you'd think. As long as the impact isn't nearly horizontal, less than about 15 degrees from the surface, the resulting crater is circular. The energy is deposited so quickly and so symmetrically that the direction of arrival becomes irrelevant. Scientists studied this by examining impact craters on the moon, where erosion doesn't erase the evidence. Out of thousands of lunar craters, only a handful are noticeably elliptical, and those correspond to impacts at very shallow angles. The rest are circular, formed by objects arriving from every possible direction. 3I Atlas. Even if it approached at a 30 or 40 degree angle, would create a round crater. Now, let's talk about what happens to the material excavated from that crater, the ejecta. In the first few seconds of impact, before the crater has finished forming, material is being thrown outward at tremendous speeds. Some of this material is vaporized, turned into gas by the heat and pressure. Some is molten melted rock that will cool into glass as it flies through the air. Some remain solid, but fractured and pulverized into dust and fragments. The ejecta follows ballistic trajectories, meaning it's thrown upward and outward like projectiles from a cannon. The fastest ejecta material ejected early in the impact, when energies are highest, can reach velocities exceeding escape velocity. That's 11.2 kilometers per second for Earth. Material moving faster than that doesn't fall back. It enters orbit or escapes into space entirely carrying with it samples of Earth's crust and possibly fragments of the comet itself. Some of this material will eventually re-enter the atmosphere days or weeks later, burning up like meteors. Some will be captured by the moon or lost to interplanetary space. In a very real sense, every large impact ejects a small portion of Earth into the cosmos. The planet becomes lighter atom by atom. The slower ejecta, still moving at hundreds or thousands of meters per second, falls back to Earth within minutes or hours. Close to the crater, within 50 to 100 kilometers, the ground is buried under an ejecta blanket, a layer of pulverized rock glass beads and shocked minerals meters to tens of meters thick. This blanket is hot. Some of it glows red. Fires ignite wherever it lands on flammable material. Farther out, the ejecta thins, becoming a rain of smaller particles. At 500 kilometers from the impact, you might experience a hail of pebble-sized fragments falling from the sky, like hail hot enough to start fires, but small enough that you could survive by taking cover. At 1,000 kilometers, the fallout is dust-fine particles that coat surfaces, turn the air gray, and settle slowly over hours. The distribution of ejecta tells a story. When geologists study ancient impact sites, they look for ejecta layers in the surrounding rock. The Chicxulub impact, for example, left a layer of debris that's now found in rock formations all over the world, a thin line marking the moment when the dinosaurs' world ended. That layer contains shocked quartz, tiny glass spherules, and elevated levels of iridium, an element rare in Earth's crust, but common in asteroids and comets. 3I Atlas would leave a similar signature. The unusual chemistry of the comet, high nickel carbon dioxide cyanide, would be detectable in the ejecta layer. Future scientists digging through sediments would find a moment in Earth's history when something foreign arrived. They would measure the isotope ratios and realize the material didn't form here. They would calculate the energy required to distribute it so widely and understand the scale of what happened. But ejecta is only part of the immediate aftermath. There's also the seismic shock. When the initial impact shock wave propagates into the Earth, it eventually transitions from a shock front, where pressure and temperature are extreme, into a more familiar seismic wave. These waves travel through the entire planet. Primary waves, or P waves, compress and expand the rock as they pass, moving at about 6 kilometers per second through the crust. Secondary waves, or S waves, shear the rock side to side, moving more slowly at about 3.5 kilometers per second. Research shows that a 1 million megaton impact would generate seismic waves equivalent to a magnitude 8 to 9 earthquake at the impact site. For comparison, the 2011 Tohoku earthquake in Japan was magnitude 9.0. It shifted the Earth's axis by about 10 centimeters, shortened the day by 1.8 microseconds, and was felt as far away as Moscow. The tsunami it generated crossed the entire Pacific Ocean, causing damage as far as Chile and Antarctica. But earthquakes and impacts are different. Earthquakes release their energy over an area, typically along a fault line, and over a duration of tens of seconds to minutes. Impacts release their energy at a single point, essentially instantaneously. The seismic signal is sharp, impulsive, unmistakable. Seismometers around the world would record it within minutes, and scientists would immediately recognize the signature. This wasn't tectonic. This was something else. Close to the impact, within 200 to 300 kilometers, the ground shaking would be catastrophic. Buildings would collapse, bridges would fall, landslides would cascade down hillsides, roads would buckle and fracture, underground pipelines, water, sewage, gas would rupture, creating secondary disasters. Dams, if present, might crack, releasing floods downstream. Farther away, the shaking would be noticeable, but less destructive. At 1,000 kilometers, you'd feel something like a magnitude 5 earthquake, strong enough to wake you if you were sleeping, strong enough to knock items off shelves, but not strong enough to collapse well-built structures. At 2,000 kilometers, it would be a subtle vibration, a sense that the ground was humming for a few seconds. But here's something subtle that most people miss. The seismic waves don't just travel through the crust, they travel through the entire planet. Some waves propagate along the surface, Rayleigh waves and love waves, which cause the rolling and shaking we associate with earthquakes. Others dive deep, passing through the mantle, and even the core, emerging on the opposite side of the Earth, the antipode, where they can trigger small earthquakes and rock falls. The Chicxulub impact, according to some research, may have intensified volcanic activity at the antipodal point, the region of the Earth directly opposite the impact site, which at the time was in what is now the Indian Ocean. The seismic energy focused at that point could have destabilized magma chambers, triggered eruptions, or caused massive lava flows. The Deccan Traps, huge volcanic formations in India that erupted around the same time as the impact, might have been intensified by seismic energy traveling through the Earth. 3I Atlas would produce similar effects, though probably less extreme. Volcanoes near the antipode might show increased activity. Geothermal areas might see changes in hot spring temperatures or geyser behavior. Sensitive instruments would detect the seismic energy circling the globe multiple times, echoing back and forth like sound in a cathedral, gradually fading but measurable for days. And then there's the question of what the crater itself looks like in the hours and days after impact. Imagine approaching it from the air, say in a helicopter or aircraft that survived the initial shockwave and managed to take off afterward. You'd see a landscape transformed beyond recognition. Where there was once plains or hills or forest, there's now a roughly circular scar miles across with walls that slope inward toward a depressed center. The walls are terraced, stepped because they collapsed in segments, each layer sliding inward like a slow-motion avalanche. The floor of the crater is flat in some places, chaotic in others. Pools of molten rock glowing red, slowly cooling. Fragments of bedrock uplifted and twisted. Boulders the size of houses ejected and then fallen back, scattered randomly. And in the very center, the central uplift, a hill made of rock that was once deep underground, now exposed to the sky, radiating heat. The air above the crater shimmers with heat. Dust and smoke obscure the details. Small fires burn where ejecta landed on any remaining vegetation. The smell would be overwhelming sulfur from vaporized rock ozone, from electrical discharges in the dust clouds, smoke from fires, and something else harder to define. The smell of violence, of geology accelerated to timescales human senses aren't designed to process. For comparison, consider Meteor Crater in Arizona, Barringer Crater as it's formerly known. It's about 1.2 kilometers across and 170 meters deep, formed roughly 50,000 years ago by an iron meteorite about 50 meters in diameter. Today, after millennia of erosion, it's still dramatically visible. The rim stands 50 meters above the surrounding plain. You can hike down into it carefully with permission and touch rocks that were once hundreds of meters underground. Scientists estimate that when Barringer Crater formed, it excavated approximately 175 million tons of rock. The surrounding area, out to a radius of several kilometers, was buried under ejecta. Trees, if any, existed in that arid region, would have been flattened or incinerated. Animals would have died from the shockwave, the heat, or the fallout. And that was a tiny impact, perhaps 10 megatons, roughly the size of a large nuclear weapon. 3I, Atlas, is 100,000 times more energetic. The crater would be proportionally larger, deeper, more complex. And it would take not thousands of years, but millions for erosion to soften its edges and fill it with sediment. Craters age slowly. The youngest large crater on Earth is probably Kali in Estonia, formed about 4,000 years ago by a meteorite that broke into fragments. It's only 110 meters across, and already vegetation has reclaimed it. The rim is forested. The floor holds a small lake. If you didn't know it was an impact crater, you might think it was just an unusually round valley. Larger craters take longer. Barringer Crater still looks fresh after 50,000 years because Arizona's climate is dry and erosion is slow. In wetter climates, craters disappear faster. The Rice Crater in Germany, 24 kilometers across and 15 million years old, is barely recognizable from ground level. You'd need satellite imagery or geological surveys to notice it. The landscape has been eroded, filled, forested, farmed. Only the subtle curve of the land and the presence of shocked minerals reveal its origin. 3I Atlas's crater would follow a similar path. In the first years, it would be raw, harsh, lifeless. The rock would cool slowly, taking decades for the deepest molten pools to fully solidify. Rain would fill the lowest points, creating lakes initially sterile, devoid of life, but eventually colonized by algae, bacteria, and microorganisms carried by wind or migrating birds. Over centuries, sediment would wash in from the eroding crater walls. Soil would form. Plants would take root, first the hardy pioneers, grasses, lichens, shrubs, then eventually trees. Animals would return. The crater would become an ecosystem unique because of its geology, its shape, its history. And millions of years later, long after humans are gone or change beyond recognition, geologists of whatever species inherits the Earth would study this crater. They would drill cores, analyze minerals, date the rocks. They would piece together the story, an object from interstellar space moving at impossible speed, arriving on a day when the planet wasn't expecting visitors. They would measure the energy, calculate the devastation, and perhaps wonder whether anyone survived to witness it. But survival isn't determined only by proximity to the crater. The immediate destruction, the thermal pulse, the shock wave, the ejecta is regional. deadly within hundreds of kilometers, noticeable within thousands, but not globally lethal. The real question is what comes next. Because the crater, as terrible as it is just the wound. The infection, the long-term consequences, spreads much farther and lasts much longer. The sky doesn't return to normal, not for months, maybe not for years. In the days after impact, as fires burn and dust settles, and survivors try to comprehend what happened, something quieter begins a change in the light itself. Sunsets become unusually vivid, painted in reds and purples that seem almost artificial. The moon, when it rises, looks dimmer, as though seen through gauze. And slowly, imperceptibly at first, the temperature begins to drop. This is the atmosphere remembering. And in that memory, written in particles too small to see, is a story about how fragile warmth really is. When 3I Atlas struck the Earth, it didn't just excavate rock and release energy. It injected material into the upper atmosphere, the stratosphere, where normal weather doesn't reach. Dust from the pulverized crust, soot from wildfires, aerosols from vaporized comet ice. All of it lifted by the violence of impact, by the heat of fires, by convection currents that carried it upward like smoke from a chimney, but at a scale that turns regional disaster into global consequence. The stratosphere begins about 10 to 15 kilometers above sea level, depending on latitude. It's a stable layer. Temperature increases with altitude there, which prevents vertical mixing. That's why weather happens in the troposphere below, but not in the stratosphere above. Air that enters the stratosphere tends to stay there, circulating slowly, taking months or years to settle back down. Research shows that fine particles in the stratosphere, anything smaller than about 10 micrometers, about 1/10, the width of a human hair, can remain suspended for extended periods. They scatter and absorb sunlight, reducing the amount of solar energy reaching the surface. The effect is subtle at first, but cumulative. A 1% reduction in sunlight might not sound significant, but sustained over months, it translates into measurable cooling. Scientists estimate that 3I Atlas would inject somewhere between 100 and 500 cubic kilometers of fine dust and aerosols into the stratosphere. That's a range, not a precise number, because the exact amount depends on impact angle target geology and how much material is pulverized finely enough to stay aloft. But even at the lower end of that estimate, it's enough to matter. For comparison, consider volcanic eruptions, nature's closest analog to impact events. When Mount Pinatubo in the Philippines erupted in 1991, it injected approximately 20 million tons of sulfur dioxide into the stratosphere. That SO2 combined with water vapor to form sulfuric acid aerosols, tiny droplets that reflected sunlight. The result was a global temperature drop of about 0.5 degrees Celsius over the following year. Sunsets turned brilliant crimson. The ozone layer thinned temporarily. Agricultural yields dropped in some regions due to reduced sunlight and cooler growing seasons. Pinatubo was one of the largest eruptions of the 20th century, and it cooled the planet measurably for about 2 years before the aerosols settled out. Now scale that up by a factor of 10 or 100. 3I's Atlas doesn't inject sulfur dioxide. It injects solid particles, dust, and soot, which are even more effective at blocking light. The cooling could be more pronounced and longer lasting. The term scientists use is impact winter, a period of reduced sunlight and lower temperatures following a large impact. It's similar to nuclear winter, the hypothetical climate effect that would follow a large-scale nuclear war, where smoke from burning cities blocks sunlight for months or years. Both scenarios involve the same basic physics: put enough particles in the stratosphere and the planet cools. The Chicxulub impact 66 million years ago produced an impact winter that may have lasted a decade or more. Scientists suggest that global temperatures dropped by as much as 10 to 15 degrees Celsius in the first few years. Photosynthesis on land and in the oceans declined sharply. Plants that survived the initial fires and shockwaves then faced months of dim, cold conditions. Herbivores starved. Carnivores that depended on herbivores starved in turn. The food chain collapsed from the bottom up. 3I Atlas being smaller wouldn't produce cooling on that scale. But even a reduction of 2 to 5 degrees Celsius sustained for a year or two would have profound effects. Let's walk through what that means, step by step. First, sunlight. Within weeks of the impact, observers around the world would notice that the sun appears dimmer, slightly reddish even at noon. The sky takes on a hazy, milky quality. Stars become more visible at night because atmospheric scattering, the process that normally makes the sky blue, is reduced. The light that does reach the surface is diffuse, shadowless, like an overcast day that never ends. Photosynthesis depends on sunlight. Plants use light energy to convert carbon dioxide and water into glucose and oxygen. Reduce the light by 20 or 30%, and photosynthesis slows proportionally. Trees and crops don't die immediately, they're resilient, but their growth rate decreases. Leaves produce less sugar. Roots store less energy. Over weeks and months, this adds up. Agricultural systems, which are already optimized for current climate conditions, would be hit hard. Crops like wheat, rice, and maize have specific sunlight and temperature requirements. Cool the planet by a few degrees, reduce sunlight by a quarter, and yields drop significantly. In temperate regions, the growing season shortens. In tropical regions where agriculture depends on consistent warmth, even a small temperature drop disrupts planting cycles. Historical examples give us a sense of the human consequences. The eruption of Mount Tambora in Indonesia in 1815 led to the year without a summer in 1816. Global temperatures dropped by about 0.4 to 0.7 degrees Celsius. That doesn't sound like much, but it was enough to cause widespread crop failures across Europe and North America. Snow fell in June in New England. Frosts occurred in July. Wheat and corn harvests failed. Food prices skyrocketed. Tens of thousands died from starvation and disease. And that was from a volcanic eruption with far less energy than 3I Atlas. The cooling was regional, not global, and it lasted only 1 year. An impact winter from 3I Atlas could affect the entire planet for multiple growing seasons. Food storage becomes critical. Modern agricultural systems are efficient, but not particularly resilient. We grow food seasonally and store some reserves, but those reserves are measured in months, not years. Global grain stocks, the buffer that prevents famine during bad harvests, typically amount to about 70 to 90 days of consumption. That's barely 3 months. If harvests fail 2 or 3 seasons in a row, reserves run out quickly. There would be cascading effects. Livestock depends on feed crops. If corn and soy harvests drop, livestock production drops. Meat becomes scarce and expensive. Dairy products follow. Food that remains available becomes subject to hoarding speculation and political control. International trade, which normally smooths out regional shortages, might break down as nations prioritize domestic needs. Historical famines teach us that the social and political consequences of food scarcity are often worse than the scarcity itself. The Great Famine in Ireland from 1845 to 1852, triggered by potato blight, killed about 1 million people and forced another million to emigrate. But Ireland was still producing food. During the famine, it exported grain and livestock to England, even as its own population starved. The problem wasn't absolute scarcity. It was distribution economics and policy failure. After an impact winter, similar dynamics would emerge. Some regions would fare better than others. Tropical areas, which depend on consistent warmth, might suffer more than temperate regions, which are adapted to seasonal variation. Coastal areas buffered by ocean heat might maintain more stable temperatures than continental interiors. But everywhere food production would decline, and the global system that moves food from surplus areas to deficit areas might struggle or collapse. Now, let's talk about what happens to the oceans because they're not immune to impact winter. Oceans absorb and store heat much more effectively than land. They also circulate, distributing warmth from the equator toward the poles. This thermohaline circulation, driven by differences in temperature and salinity, is what prevents Earth's climate from being even more extreme than it already is. The Gulf Stream, for example, carries warm water from the Caribbean to northern Europe, keeping places like London and Paris much warmer than they would be otherwise. Impact winter disrupts this system. Reduced sunlight means less heat absorbed by the ocean's surface. Cooling surface waters become denser and sink, which can alter circulation patterns. Research shows that large climate perturbations, whether from impacts, volcanic eruptions, or other causes, can shift ocean currents, temporarily changing weather patterns in unpredictable ways. Marine ecosystems are also photosynthesis dependent, but in the oceans, the primary producers are phytoplankton, microscopic algae that drift in the sunlit surface waters. These organisms form the base of the marine food web. Fish eat zooplankton that eat phytoplankton. Reduce the sunlight and phytoplankton populations decline. Zooplankton populations follow. Fish stocks drop. Fisheries collapse. Coastal communities that depend on seafood face shortages. There's also the question of ocean acidification. We mentioned earlier that impacts generate nitrogen oxides, which form acid rain. When that rain falls into the ocean, it slightly lowers the pH of surface waters. Combined with reduced photosynthesis, which normally removes CO2 from the water, the ocean becomes more acidic. Organisms with calcium carbonate shells or skeletons, corals, mollusks, some plankton struggle to build and maintain their structures in acidic conditions. The Chicxulub impact is thought to have caused severe ocean acidification. Fossil records show a sudden decline in species with calcium carbonate shells immediately after the impact. Recovery took hundreds of thousands of years. 3I Atlas wouldn't cause damage on that scale, but it would stress marine ecosystems already facing challenges from modern industrial activity, overfishing, and climate change. And then there's the aerosol chemistry, what happens chemically in the stratosphere while all this dust is circulating. Sulfate aerosols from volcanic eruptions are relatively well understood. They form droplets, reflect sunlight, and eventually fall out as acid rain. But dust from an impact is more complex. It includes silicate minerals, metal oxides, carbon particles from fires, and possibly exotic compounds from the comet itself. Nickel vapor, cyanide, carbon dioxide, ice. Research shows that these particles can catalyze chemical reactions that wouldn't normally happen in the stratosphere. One concern is ozone depletion. The ozone layer located in the stratosphere at altitudes of 15 to 35 kilometers absorbs ultraviolet radiation from the sun. Without it, surface UV levels would increase dramatically, causing skin cancer, cataracts, and damage to plants and plankton. Certain chemical reactions on the surface of stratospheric particles can break down ozone molecules. Volcanic eruptions sometimes cause temporary ozone thinning. An impact could do the same, but more severely. If UV levels increase by 20 or 30% for several months, the effects would be noticeable. Humans could adapt by staying indoors during peak sunlight or wearing protective clothing. But ecosystems can't adapt that quickly. Phytoplankton near the ocean surface would be damaged. Amphibians, which have permeable skin, would suffer. Insects, many of which are sensitive to UV, might decline. The ecological disruption would compound the effects of reduced sunlight and cooling temperatures. There's also the visual and psychological impact of a changed sky. Humans are deeply attuned to light and weather. We notice when the sun looks different. We feel uneasy when the sky stays hazy for weeks. Historical accounts from years following major volcanic eruptions describe people's discomfort with the altered light, the strange colors, the dim days, the sense that something fundamental about the world had shifted. After Krakatoa erupted in 1883, The sunsets were so vivid that people in Europe and North America thought their cities were on fire. Newspapers received reports of distant conflagrations that didn't exist. Artists painted the skies trying to capture colors they'd never seen before. Edvard Munch's painting, The Scream, with its turbulent blood-red sky, is thought to have been influenced by the atmospheric effects of Krakatoa. Imagine that sustained for months. Imagine children growing up during impact winter, seeing a sun that doesn't quite look like the sun, experiencing seasons that don't follow the normal patterns. There would be psychological effects, increased anxiety, disrupted sleep cycles, seasonal affective disorder on a mass scale. These are subtle compared to starvation and infrastructure collapse, but they matter. Human well-being depends on more than just food and shelter. It depends on a sense of normalcy, of predictability, of a world that behaves the way we expect it to. Recovery would be gradual. Stratospheric particles eventually settle or are washed out by precipitation. Soot and fine dust fall first within months. Aerosols and the finest particles last longer, up to 2 or 3 years. Slowly, sunlight returns to normal levels. Temperatures begin to rise, plants recover, agricultural yields improve, but the recovery isn't uniform. Some ecosystems bounce back quickly, others don't. Species that were already struggling, those with narrow environmental tolerances, those confined to small habitats, might go extinct. Ecosystems that lost key species, pollinators, keystone herbivores, apex predators might reorganize into different configurations. The world that emerges after impact winter isn't the same as the world before. Scientists call this ecological succession. After a disturbance, fire, flood, volcanic eruption, impact, new species colonize the affected area. Pioneer species arrive first, those adapted to harsh conditions. Gradually, as soil rebuilds and conditions stabilize, more complex communities develop. Forests regrow. Animal populations recover. But the process takes decades to centuries, and the end result often looks different from the starting point. The Chicxulub impact, for example, didn't just kill the dinosaurs, it restructured entire ecosystems. The forests that existed before the impact, dominated by conifers and cycads, were replaced by angiosperm forests, flowering plants that spread rapidly in the aftermath. Mammals, which had been small and mostly nocturnal during the age of dinosaurs, diversified and grew larger. Birds, the descendants of small feathered dinosaurs, inherited the skies. The impact didn't just subtract species, it reshuffled the deck, creating opportunities for survivors. 3I's atlas wouldn't trigger a mass extinction, but it would create openings. Invasive species might spread into areas where native species were weakened. Agricultural pests, some of which thrive in disturbed environments, might become more problematic. Disease vectors, mosquitoes, ticks, rodents might shift their ranges in response to changing temperatures and disrupted ecosystems. And through all of this, the dust would continue to settle, literally. Fine particles falling from the stratosphere, coating surfaces, mixing into soil, washing into rivers and oceans. For years after the impact, you could collect samples from remote areas, glaciers, deep ocean sediments, lake beds, and find elevated levels of shocked minerals, nickel, and other markers of the event. The planet would carry the signature in its ice cores and sediment layers, a thin line marking the moment when something from outside arrived and left its mark in more ways than one. Think about the interplay of scales here. The impact lasts seconds. The crater forms in minutes. The fires burn for days. The dust circulates for months. The cooling persists for years. The ecological recovery takes decades. The geological scar lasts millions of years. Each time scale matters. Each layer of consequence builds on the one before. This is what impact winter means, not just cold, not just dark, but a slow unraveling of systems that depend on stability. Agricultural systems, economic systems, social systems, ecological systems, All of them stress simultaneously, all of them trying to adapt to conditions that haven't existed in human memory, maybe not in human history. And yet life doesn't end. It adjusts. It survives. Not all of it, not everywhere, but enough. Because Earth has been through this before, and the biosphere, the sum total of all living things, has a kind of resilience that comes from deep time, from 4 billion years of surviving impacts, eruptions, climate shifts, mass extinctions. Life persists not because it's strong, but because it's flexible, diverse, opportunistic. But survival isn't the same as comfort. And the question we've been building toward throughout this journey isn't just whether humanity would survive an impact like this, it's how we would respond in the moment, in the days and weeks, when the dust was still rising and the full scale of what happened was only beginning to reveal itself. The first warning wouldn't come from the sky. It would come from a computer screen in a small office somewhere, showing a data point that shouldn't exist. We've built systems to watch for exactly this kind of threat. Networks of telescopes scanning the night sky, algorithms comparing images taken hours apart, searching for anything that moves in ways asteroids and comets shouldn't. These systems exist because we've learned slowly recently that the universe isn't empty and space isn't safe. We've learned to pay attention. And in the case of 3I Atlas, we did. On July 1st, 2025, the Atlas Telescope Network in Chile detected a faint object moving unusually fast. Within 24 hours, astronomers confirmed it was interstellar. Within 48 hours, orbital calculations showed it posed no danger to Earth. It would pass at 1.8 astronomical units, roughly 270 million kilometers away. Safe, harmless, a gift of data, not a threat. But let's rewrite that story. Let's say the trajectory was different. Let's say the calculations run and rerun by computers and checked by human astronomers showed something else. A close approach, an intersection, a collision course. What happens then? How much time do we have, and what can we possibly do with it? Modern detection systems are good, but they're not perfect. Research shows that objects the size of 3I Atlas, 1 to 2 kilometers across, can be detected at distances of several 100 million kilometers if they're actively brightening, as comets do when approaching the sun. That gives us a detection window of perhaps 6 months to a year before impact, depending on the trajectory and how reflective the object is. 6 months sounds like a lot of time. It's not. The first days after detection would be consumed by verification. Is the data correct? Could there be an error in the orbital calculations? Astronomers would take additional observations, refining the trajectory, calculating the uncertainty. The object's position is known to within a certain margin of error, a region of space, not a point. As more observations come in, that region shrinks. The trajectory becomes clearer. Within a week, the uncertainty would be small enough to know, with confidence, impact is likely. Not certain nothing in orbital mechanics is absolutely certain until it happens, but probable enough that governments need to be informed. And this is where things get complicated, because the response to an existential threat isn't just technical, it's political, social, psychological. Who gets told first? How is the information released? Do you announce it immediately, risking panic, or do you wait until you're certain, risking accusations of cover-up? Historical parallels are limited, because humanity has never faced a confirmed impact threat of this scale. The closest analog might be the Cuban Missile Crisis in 1962, when nuclear war seemed imminent. For 13 days, the world's leaders negotiated, while the public remained largely unaware of how close catastrophe was. Information was tightly controlled. Only afterward did people understand what had almost happened. But an asteroid impact can't be negotiated away. It's not political, it's physics. And in the age of social media, information, accurate or not, spreads faster than any government can control. Someone somewhere would leak the trajectory data. Amateur astronomers would confirm it independently. Within days, the world would know. The question is, what does the world do with that knowledge? Option 1, deflection. Change the asteroid's trajectory so it misses Earth. This is the preferred solution the one space agencies have been developing for decades. NASA's DART mission in 2022 successfully demonstrated that a spacecraft could alter an asteroid's path by impacting it at high speed. The test changed the target asteroid's orbital period by about 33 minutes, enough to prove the concept works. But DART was a small asteroid, and the spacecraft had years to reach it. 3I Atlas is different. It's larger, it's faster, and crucially, it's moving on a hyperbolic trajectory from interstellar space. That means it's not in orbit around the sun, it's just passing through. You can't wait for an orbital alignment. You can't plan a mission years in advance. You have to intercept it while it's incoming, which is far more difficult. Scientists estimate that deflecting an object the size of 3I Atlas would require changing its velocity by at least a few centimeters per second, enough to make it miss Earth by a safe margin. That doesn't sound like much, but momentum equals mass times velocity. A 2-kilometer comet with a mass of billions of tons requires an enormous impulse to change its path measurably. Nuclear weapons are often proposed for this scenario, not to destroy the asteroid, which would just create multiple impacts instead of one, but to vaporize material on one side, creating a rocket-like thrust that pushes the object in the opposite direction. Research shows this could work in theory. The Soviet Union and the United States both developed nuclear-tipped missiles during the Cold War that could, with modifications, be launched toward an asteroid. But there are problems. First, you need months to plan, build, and launch a mission. 6 months of warning might not be enough, especially if the object is approaching from a direction that makes interception difficult. Second, nuclear weapons in space are banned by international treaty, the Outer Space Treaty of 1967. Using them would require international consensus, which takes time that we don't have. Third, and most critically for 3I Atlas speed. Objects from our solar system approach Earth at typical velocities of 15 to 25 kilometers per second. 3I Atlas is moving at 58 kilometers per second, more than twice as fast. That makes interception trajectories much harder to calculate and requires far more fuel to match velocities. Any spacecraft sent to intercept it would need to be launched quickly, accurately, and with enough payload to actually change the comet's course. The grim reality is that with current technology and 6 months of warning, deflection probably isn't feasible. Not for an object this large, this fast, coming from this angle. We could try, we'd have to try, but success would be unlikely. Plans would be made, rockets would be prepared, engineers would work around the clock, and the world would watch, hoping, knowing that hope might not be enough. So, what's option 2? If we can't move the asteroid, we move ourselves. Evacuation. For an impact of this scale, the immediate danger zone, the area where survival is unlikely, extends perhaps 500 to 1,000 kilometers from the projected impact site. That's roughly the size of Texas or France or a large portion of any continent. Tens of millions of people potentially, depending on where the impact occurs. Could you evacuate that many people in 6 months? Logistically, maybe. Practically, it depends on infrastructure governance and social cohesion. In wealthy nations with good transportation networks, you could move most people out of the danger zone if you started immediately and maintained order. In developing nations or in regions with political instability, it would be much harder. Historical evacuations provide some guidance. In 1991, before Mount Pinatubo erupted, approximately 60,000 people were evacuated from the surrounding area, based on warnings from volcanologists. The evacuation likely saved tens of thousands of lives, but that was a localized event, and people could return home within weeks or months. Hurricane Katrina in 2005 prompted the evacuation of over 1 million people from New Orleans and surrounding areas. Most left voluntarily or under mandatory orders before the storm hit. But many, particularly the poor, the elderly, those without transportation, couldn't or didn't leave. When the levees broke and the city flooded, thousands were stranded. Over 1,800 died. The social fabric tore. Recovery took years. Now, imagine an evacuation order covering an area 10 times larger, affecting 50 times as many people, with a deadline measured in months, but a certainty of complete destruction. Where do people go? Who feeds them? Who houses them? What happens to homes, businesses, pets, possessions left behind? What happens to hospitals, prisons, power plants? And critically, what happens to people who refuse to leave? Some would stay out of disbelief, attachment, defiance, or simple inability to imagine abandoning their lives. History shows that some people always stay even when danger is certain. They die, and the world moves on without them. There's also the question of panic versus order. Would society hold together during the evacuation, or would it fracture? Would people help each other, or would it devolve into chaos, research into disaster? Psychology shows that humans usually cooperate during emergencies, contrary to popular myths about panic and looting. Most people become more pro-social, more willing to help strangers when faced with shared danger. But that cooperation depends on maintaining trust in institutions and leaders and the belief that someone is in control and has a plan. If that trust breaks, if governments are seen as incompetent, dishonest, or indifferent, cooperation gives way to self-interest. People hoard supplies, they arm themselves, they stop following rules. The disaster becomes worse because the social glue that holds communities together dissolves. One thing we know with certainty: communication matters. Clear, honest, consistent information reduces panic. Lies, even well-intentioned ones, increase it. During the Fukushima nuclear disaster in 2011, inconsistent messages from government officials and the power company eroded public trust. Rumors filled the vacuum. Some people fled unnecessarily. Others stayed when they should have left. The confusion amplified the suffering. For an asteroid impact, transparency would be essential but difficult. How do you tell people they have 6 months to live, or that their city will be destroyed, or that global food systems might collapse without triggering despair? How do you maintain hope while being honest about the scale of what's coming? Let's also consider the global effects beyond the immediate impact zone. Even if you're 5,000 kilometers from the impact site, far enough to avoid the shockwave, the ejecta, the fires your life changes. Supply chains break. Food becomes scarce. Governments focus resources on disaster response, leaving other needs unmet. Refugees from the impact zone arrive needing shelter, food, medical care. Social tensions rise. In the months following impact, as impact winter sets in and temperatures drop, agriculture struggles everywhere. International cooperation becomes critical. Countries with food surpluses would need to share with those facing shortages. But would they? History suggests that nations prioritize self-interest, especially in times of scarcity. Trade barriers go up. Hoarding begins. The world fractures into regions of relative stability and regions of chaos. There's a philosophical question embedded here. What do you do with knowledge of inevitable disaster? Do you spend the remaining months trying to prevent it, even if the odds are slim? Do you evacuate and rebuild, accepting loss, but preserving life? Do you simply live as normally as possible, refusing to let fear consume the time that's left? Different people would answer differently. Some would throw themselves into work, building, preparing, doing anything that feels productive. Others would turn to family, spending final months with loved ones. Some would seek spiritual comfort. Others would descend into nihilism or hedonism if the world is ending. Why not abandon restraint? And what about the children? How do you explain to a child that their future has been shortened by an object from space they can't see and don't understand? Parents would face impossible choices, whether to shield children from the truth or prepare them for what's coming. Schools would struggle to function. Some teachers would continue lessons maintaining normalcy. Others would abandon curricula and simply be present, offering comfort. Here's a thought that keeps emerging in disaster research. Humans are remarkably adaptable. We adjust to circumstances that seem unbearable. During World War II, people in besieged cities, Leningrad, London, Berlin, continued daily life even as bombs fell. Children played in rubble, couples married, babies were born. Life insisted on itself even when death was close. The same would happen before and after impact. Markets would still open, though goods would be scarce. Music would still play. People would still fall in love, laugh at jokes, watch sunsets. Not because they're in denial, but because that's what humans do. We persist. We find meaning in small things. We refuse to let catastrophe have the final word. After the impact, survival would depend on preparation, location, and luck. Those far from the impact zone with access to food stores and shelter would have the best chance. Communities that cooperated, shared resources, and maintained order would fare better than those that fractured. Knowledge of agriculture, engineering, medicine, basic survival skills would become invaluable. And in the longer term, after the dust settled and the cooling stabilized, humanity would rebuild. Not in the same way, not in the same places, but rebuild nonetheless, because that's the pattern throughout history. Civilizations fall, cities burn, plagues kill millions. And yet, life continues. Knowledge is preserved, new generations emerge, the species endures altered but unbroken. Would we learn from it? That's harder to say. Disasters sometimes teach lessons better. Building codes after earthquakes, improved warning systems after tsunamis. But they also fade from memory as time passes. Generations born after the event don't carry the same visceral understanding. The urgency fades, old habits return. Still, an interstellar impact would be different. It would enter human mythology, the collective memory that shapes cultures for centuries. It would become a reference point before the impact, after the impact. Stories would be told. Monuments would be built. Children would learn about the day the sky fell and what came after. But we're speaking hypothetically. 3I Atlas didn't hit Earth. It passed at a safe distance, a reminder rather than a reckoning. We watched it with telescopes, studied its chemistry, marveled at its strangeness, and then watched it leave, disappearing back into the dark from which it came. We were lucky. We remain lucky. The question is whether that luck will hold, or whether someday, maybe not in our lifetimes, but someday the warning will come, and the trajectory will show no miss-only arrival. And in facing that possibility, even hypothetically, we learn something about ourselves, about our fragility and resilience, about what we value and what we're willing to fight for, about the strange grace of being alive on a small planet in a dangerous universe. The impact never happened, but the question lingers, patient and quiet, like starlight traveling through emptiness. We've walked a long path together through this quiet night. We've stood at ground zero of an impact that never happened. We've watched light turn to fire, felt shockwaves travel through continents, seen dust rise into an atmosphere that remembers everything. We've traced the journey of a visitor from elsewhere, 7 billion years old, moving faster than anything from our neighborhood, carrying chemistry, written in a different stellar nursery. And now, as we near the end, let's return to where we started. July 1st, 2025, a telescope in Chile, a data point that changed our understanding just slightly, just enough. 3I Atlas passed us safely. On December 19th, 2025, it reached its closest approach to Earth, 270 million kilometers away, 1.8 times the distance to the Sun. You couldn't see it without a telescope. It didn't make the evening news. Most people never knew it was there. And yet, for those who are watching, astronomers, planetary scientists, anyone who understands what interstellar objects represent, it was profound. Because here's what 3I Atlas taught us. Even in passing, we are not alone in receiving visitors. Every star system sheds material. Every planetary system ejects comets and asteroids into the space between stars. The galaxy is filled with wanderers, ancient and cold, carrying stories from places we'll never see. Some of them pass through our neighborhood. A few, very few, we manage to detect. Most slip by, unnoticed, invisible, like ships passing in the night on an ocean too vast to comprehend. The fact that we saw 3I Atlas at all is remarkable. It required decades of technological development, international cooperation, funding for telescope networks, algorithms sophisticated enough to distinguish moving objects from background stars, and scientists willing to spend their careers watching the sky for things that might never come. We built those systems not knowing if they'd ever find anything. And then they did. 3 times now. 3 interstellar objects in 8 years. That's not a large sample size, but it suggests something important. Interstellar objects are not rare. They're common. Research shows that there might be trillions of them in the Milky Way. At any given moment, comets and asteroids ejected from their birth systems, drifting through the dark, occasionally passing near a star. We're only now developing the ability to see them. The Vera C. Rubin Observatory, scheduled to begin operations, soon will scan the entire visible sky every few nights. Scientists estimate it might detect dozens of interstellar objects per year, maybe more. Each one will be different. Different chemistry, different size, different velocity. Each one a data point, helping us understand how other star systems form, how planets interact with comets, how material spreads through the galaxy. It's like receiving letters from distant places written in the language of physics and chemistry. We can't visit those places, but the letters come to us if we're patient enough to wait and attentive enough to read them. And in learning to read those letters, we've also learned something about danger. Because while 3I Atlas was safe, the next visitor might not be, or the one after that, or the one 1,000 years from now. The universe doesn't schedule its threats for our convenience. Impacts happen on geological timescales, which means they're rare from a human perspective, but inevitable from a planetary perspective. Earth has been struck before, many times. The craters, though, eroded remain. The chemical signatures and rock layers mark moments of violence that reshaped ecosystems. The Chicxulub impact 66 million years ago. The Vredefort impact 2 billion years ago. Dozens of others, large and small, spanning Earth's history. Each one changed the planet. Some caused mass extinctions. Others were regional disasters. A few, like Tunguska, occurred so recently that people alive today could have met survivors if survivors had existed in that remote Siberian forest. But here's the subtle shift in understanding that's happened in just the past few decades. We're no longer passive. We're no longer just waiting for the sky to fall. We're watching. We're planning. We've just started to develop the capability to protect ourselves. The DART mission proved we can change an asteroid's trajectory. The planetary defense networks, Atlas pan stars. Future systems like Rubin give us early warning. International cooperation, though imperfect, has improved. Space agencies share data. Governments fund research. Engineers design missions. The infrastructure of protection is being built piece by piece, telescope by telescope. It's not complete. It's not foolproof. An object like 3I Atlas arriving at interstellar velocity with only months of warning would still be beyond our current ability to deflect. But give us a decade or two, and the answer might be different. Technology improves, launch capabilities expand, nuclear propulsion, once theoretical, is being seriously developed. Space-based interceptors, once science fiction, are being modeled and tested. We're living in the first moment in Earth's 4.6 billion year history, when a species has the potential, not yet the certainty, but the potential to prevent its own extinction by impact. That's not a small thing. That's a threshold. A line crossed between being subject to the universe's whims and having some agency, some say, in our continued existence. But let's not overstate it. We're still small, still fragile, still living on a thin shell of breathable air, wrapped around a rock in a vast and largely indifferent cosmos. One good impact, one large enough and fast enough, could still end everything we've built. The cities, the art, the literature, the accumulated knowledge of millennia, all of it could be erased in an afternoon, buried under dust and fire and geological time. And maybe that's okay. Not in the sense that we should accept it passively, but in the sense that we should carry that knowledge lightly. Knowing we're vulnerable makes existence more precious. Every quiet night, every sunrise, every ordinary moment becomes a gift, not because it's dramatic, but because it could have been otherwise. We exist in a narrow window between too hot and too cold, too much radiation and too little atmosphere, too many impacts and just enough stability for life to flourish. Have you ever looked up at the night sky and felt small? Most people have. It's a common experience, almost universal. The stars are so far away, so numerous, so indifferent to our concerns. We're brief, we're tiny, we're ephemeral, and yet, and this is the paradox at the heart of everything, we're the part of the universe that looks up and wonders. We're the mechanism by which the cosmos becomes aware of itself. Carl Sagan said it beautifully. We are a way for the universe to know itself. The atoms in your body were forged in stars that died billions of years ago. You are quite literally made of stardust. And so is 3I Atlas. Different stardust from a different star, but the same fundamental process. Nuclear fusion in stellar cores, creating heavier elements, distributing them through space when stars die, gathering them into new clouds that collapse into new stars and planets and comets. Everything is connected. Everything is recycled. The universe is one story told in many chapters. 3I Atlas came from one chapter we'll never read. It passed through our chapter briefly a guest at the edge of our awareness, and then continued on toward chapters yet to be written. Maybe it will pass another star in 1,000,000 years. Maybe someone will be there to see it, to study it, to wonder where it came from. Maybe they'll calculate its trajectory and realize it once passed through a small yellow star's system, where a planet covered in water and life briefly took notice. Or maybe not. Maybe it will drift forever, silent and frozen, a monument to no one, carrying its cargo of ancient ice into depths where even starlight fades. The universe is full of such monuments, objects that witness things no one will ever know, that carry information no one will ever decode. They exist anyway, patient and complete, needing no audience. But we're different. We need stories. We need meaning. We look at 3I Atlas and see not just a comet, but a messenger. We ask not just what it is, but what it means. And in asking, we create something. The universe doesn't provide purpose. The purpose isn't grand. It doesn't come from destiny or fate or cosmic design. It comes from us, from the simple act of paying attention, of caring, of trying to understand. We build telescopes because we want to see. We calculate trajectories because we want to know. We imagine impacts because we want to prepare. We tell stories because we want to remember. And in all of that, the watching, the calculating, the imagining, the remembering, we're doing something remarkable. We're fighting entropy with consciousness. We're insisting that our brief existence matters even though the stars don't care. We're creating pockets of order and meaning in a universe that tends toward chaos. That's not nothing, that's everything. So, what do we take from this thought experiment, this journey through hypothetical catastrophe? Not fear, I hope. Fear is easy. Fear is the default response to threats we can't control. But fear alone doesn't build telescopes. It doesn't launch missions. It doesn't inspire the long, patient work of watching the sky year after year for dangers that might never arrive. What we need instead is something quieter: respect, humility, wonder. The understanding that we live in a universe that is beautiful and dangerous in equal measure. That our safety is not guaranteed, but neither is our extinction inevitable. That we have some agency, some ability to respond if we're wise enough to use it. We need to keep watching, keep building detection systems, keep funding planetary defense. Keep cooperating across borders, because impacts don't respect national boundaries, and neither should our response to them. We need to remember that we're all on this small planet together, sharing the same thin atmosphere subject to the same cosmic hazards. And we need to live fully, presently, gratefully in the time we have. Because whether or not an impact comes in our lifetimes, our time is finite anyway. We're all on borrowed time, all of us from the moment we're born. The question isn't whether we'll face an ending, but how we spend the middle. 3i Atlas reminded us of that. Not by threatening us, but by existing, by showing up from elsewhere, moving through our neighborhood at impossible speed, and then leaving indifferent to our fears and fascinations. It was here, and then it wasn't. Just like us, just like everything. But while we're here, we can look up, we can wonder, we can ask questions and seek answers. We can build things that outlast us. Knowledge art systems of protection stories told softly in the dark. We can be brave enough to imagine worst-case scenarios and wise enough to prepare for them without letting them consume us. That's the balance. That's the space between fear and wonder. And that's where we live, all of us, every day, whether we think about interstellar comets or not. So, tonight, if the sky is clear where you are, maybe step outside, look up, find a star, any star. Remember that it's not alone. Around it might be planets, comets, civilizations, stories we'll never hear. And remember that some of those comets, millions of years from now, might pass by another star, might be seen by other eyes, might inspire other minds to wonder what else is out there moving through the dark. We're part of that. We're participants in a galaxy-wide conversation conducted at the speed of light and the patience of geological time. We sent Voyager out with a golden record carrying sounds and images from Earth, hoping someone might find it someday. We search for signals from other civilizations, listening for voices in the cosmic static. We study interstellar visitors, reading the chemistry of distant suns. We're reaching out. We're paying attention. We're refusing to live in isolation on our small rock, pretending the universe beyond doesn't exist. And in that refusal, that insistence on connection, on curiosity, on care, we're creating something beautiful. 3i Atlas is gone now. By the time you hear these words, it will be past Jupiter, heading toward the outer solar system, accelerating as the sun's gravity releases it. In a few years, it will cross the heliopause, the boundary where the sun's influence fades and interstellar space begins. And then it will be truly alone again, as it was for billions of years before it found us. But we saw it, we measured it, we wondered about it, and it changed us just slightly, just enough. Because every encounter with the unknown does that. Every visitor from elsewhere reminds us that our perspective is limited, our knowledge incomplete, our existence contingent. And somehow, impossibly, that's comforting. Because it means there's always more to learn, always more to discover, always another question, waiting beyond the ones we've answered. The universe is not done revealing itself, and we're not done watching. Thank you for staying with me through this long, quiet journey. Thank you for wondering alongside me, for imagining catastrophes that didn't happen and futures that might. Thank you for caring about comets and craters and the thin blue line of atmosphere that separates life from void. These stories matter, not because they're real, this one wasn't, but because they help us see what is real more clearly. They help us understand what's at stake. They remind us to look up, pay attention, and appreciate the remarkable unlikelihood of our existence. Sleep well tonight. Dream gently. And when you wake, if the sun is shining and the sky is blue and everything feels ordinary, remember, ordinary is extraordinary. Every peaceful day is a gift from physics and chemistry and 4 billion years of evolution and luck, pure blind cosmic luck, that we're here at all. The stars are still out there, turning hydrogen into light. Comets are still wandering between them, carrying stories and ice. And we're still here watching, wondering, waiting to see what arrives next. Good night, friend. Until the next quiet journey. Until the next story told softly in the dark. Until the next moment when we look up together and ask what if the universe doesn't answer. But the question itself, that beautiful, persistent human question, is answer enough.